Yeah, so I think we are good to start. Good morning, good afternoon, good evening, everyone. Welcome to day 2 of the summer school, Data Science Africa 2020 Kampala. So for this morning, we have Professor Thomas Dietterich and also Irene Tematelewo from Oregon State University, who are going to give a session on anomaly detection in machine learning and computer vision. Professor Dietterich, over to you.
Okay, I'm going to turn on my camera briefly just to say hello to everyone, and look forward to meeting everyone in a face-to-face meeting someday. Just to show you where I am at the moment, I'm here at Oregon State University on the west coast of the United States. But I think most of you are in East Africa and Nigeria from the statistics last night. Let me stop my video and talk about this presentation. So when people think about machine learning, they generally don't think about anomaly detection, right? The most common machine learning tasks are things like classification, right? Recognizing objects, understanding spoken words, things like this, and also regression, things like predicting profits, predicting rainfall, predicting continuous quantities. But there are many applications that involve anomaly detection, and that's where you are trying to detect novelty, things that you did not see in your training data, but you encounter them, say, after you've deployed your computer system, your software system, your software product, and now you start encountering strange and novel things. And so we want tools for that also. So it's a relatively new branch of machine learning, although it's been studied, of course, in statistics. Like most things in machine learning have been studied in statistics in earlier years. But before I go any further, my student Irene Tematelewo will be presenting, leading a tutorial. So if you have a chance, you might want to download this tutorial link now, so that it's a Jupyter notebook, so that you can have it on your machine. So I'll put this up again later, but maybe right for now you can copy it down. Because in the tutorial, we want to give you some experience using some of the anomaly detection methods that come in scikit-learn that you can use. We have a relatively small group, so please ask questions. I'll stop from time to time to answer them. But obviously the webinar format makes it difficult for me to see your hands or your faces. Let me now start and talk about use cases for anomaly detection, why we might want to have an anomaly detection system. The first use case is probably is data cleaning. Let's see, we already have some questions? Let's see. Okay, very good. Is data cleaning. So very often when you collect data in an application, there will be some corruptions in it. For example, numbers may not have been recorded correctly. This is especially true in things like medical data, where the data were only collected for purposes of maybe billing. And so the actual numbers in the health records may not have ever been checked that they're sane. And so there could be typographical errors. There could be values entered into the wrong field in a form, all those kinds of things. And so those, one hopes, will show up as surprises or unusual values in those fields. And we can use anomaly detection to find things and then follow them up manually to check them. Another big area is in fraud detection and cyber attack kinds of cases where either at training time, but also at test time after you've deployed the system, you're looking for unusual behavior that might indicate some kind of crime or or cyber attack on a system. Then the next three that I list here relate much more to questions of robustness in AI systems. So one of the big problems with AI systems and computer systems in general is that they can be very brittle and they can fail suddenly, right? They're very digital. And so one example is the problem of open categories. So if you trained a object recognition system in computer vision, for example, to recognize and say it's trained in Europe, and so it knows about bicycles and cars and so on, but it's never seen a kangaroo. Or maybe if we move to Africa, you know, it's never seen elephants or giraffes or anything like this. What does it do the first time it encounters one? It doesn't have a category for that, and so it's very likely to predict it to be one of the other categories it has, and then it might make a bad decision. And I used to just use this as a joke about kangaroos, but it turned out to be true that I think it was BMW had trained a self-driving car vision system in Europe and then took it to Australia. And it was indeed confused when the first time a kangaroo bounced across the road in front of it. Similar things have to do with novel subcategories, or another good example is in medicine, when there's a novel disease. The medical diagnosis system should realize that it's different from the things it's seen before and not classify the patient as having one of the known diseases. And the same, you can also have novel subcategories, so new subtypes of a known disease. And then the last thing is known as out of distribution detection. And that's an example where at test time, the classifier is given an instance that was collected in some different way. For instance, maybe the classifier was trained to recognize chest x-rays, but from a front view only, but instead it's given an x-ray that was taken from a side view. Or a self-driving car that was trained in clear conditions, but it needs to operate in rainy conditions. And so the sort of first goal here is to detect that something's wrong and raise an exception and say this input seems to be strange. So those are the kinds of problems that we're interested in solving. And some of the properties that they have are, well, first of all, I guess, what does it mean to be an anomaly? Because some data naturally contains outlier data points. I mean, most people are only, well, I know it in feet, only 6 feet tall or less, but then there are some people who are 7 feet tall, and you might say, well, that's an anomaly. There's an error in the data, but no, there isn't. That's people can be that tall. So we want to say, and they're just called outliers, right? Unusual extreme values. But what we want to say an anomaly is it's a data point that was generated by a process that's different than the process that's generating the nominal points. So if we have a sensor failure, an incorrectly entered data point, a fraud, that's a different process than the process that's generating what we call nominal points. We don't call them normal points because we get confused between that and the normal distribution, the Gaussian distribution. So we'll call them nominal. So from a statistics or machine learning point of view, one of the big challenges is that there is very little or even no labeled data available. Or another way of saying that is anomalies tend to be rare. Fortunately, we're not hit with 50% of our transactions being fraud. It's very low. And another problem is that anomalies may not come from a well-defined probability distribution. They may be changing with time, especially if it's a crime and the fraudsters are trying to fool the system. And there's also a problem with what we call nuisance novelty, which is things can be new in an image, but they're not important for the particular task. So especially if you're looking at something like internet traffic, because you're looking for cyber attack, there can be changes in internet traffic every day. Some new app, some new news event, and people visit a website they've never visited before, but that doesn't mean that there's some problem. So our main strategy is we don't try to model the anomalies themselves. We try to model what the nominal points look like, and then we detect the anomalies because they are outliers. So that means that we will make mistakes, especially on those 7-foot-tall people. But that's a general challenge with anomaly detection, is you do get false alarms from anomaly detection systems, and you usually need a human in the loop to look at those alarms and make decisions. Okay, so there are three main, well, maybe four main technical approaches to solving anomaly detection problems with real data. And I'll be going through these and giving some examples of each one. The first are density estimation methods. So, you know, given with a probability distribution, it may have a probability density. So if we let D be our training data, then I'll use P sub D to denote its probability density. And so P sub D of XQ will be a real valued number between 0 and, well, because it's a density, it actually can be larger than 1, but a non-negative number. And larger values are more likely and smaller values are unlikely. So if we take the negative logarithm of that, that gives us a quantity that's called the surprisal, or the surprise. And so we would be infinitely surprised if we saw something of probability 0 that would happen, right? Because the log of 0 is negative infinity, and then we negate it, we get positive infinity. So we're infinitely surprised. And if we saw something that had a probability of 1, the log of 1 is 0, and so minus 0 is 0, so we'd have 0 surprise. So we're completely unsurprised by things that have a probability of 1. So we can try to model the joint probability distribution, and I'll talk about methods for that. Then there are quantile methods, which instead of trying to model the entire probability distribution, they try to model what's called a quantile. That is a boundary around the data that contains 1 minus alpha fraction of the data. So if alpha was 0.05, that would be 95% of the data points will live inside that function, and or that function will be positive for those points and negative for the points that are outside the boundary. And so we can use an anomaly score there that's this score here. And then I'll talk about distance-based metrics. These are actually the simplest, and you'll get some practice with these, where we just, given a new data point, I call XQ the query point, the new case, we compare it to all of the data that we had inside our database and find the one that minimizes the distance. So this would be the distance to the nearest neighbor, the nearest data point in the training data. And so points that are far away from all of the data points, we would say those are more likely to be outliers, unusual points. And finally, there's some techniques called projection methods, and we'll talk about those more later. Okay, so let's look at density estimation, because this is a topic that's been studied for a long time. So if I gave you a bunch of points, my goal, a bunch of points x1 up to xn, and let's say each of these points is a vector of length d of real values. So d floating point numbers is a data point. And they might be, you know, features describing a person, like their height and their weight and their temperature and their blood pressure and things like this in a medical data set. If we assume these data have been drawn, what we say IID, so independently and identically distributed, they come from some probability distribution that is not changing over time, and each data point is an independent, is a new person, they're all different, then we can think of that distribution as having some probability density, and we want to estimate this probability P over the data. And of course, P needs to be non-zero, non-negative everywhere, and the integral over, if we integrate it with respect to x, it should integrate to 1, or if it was discrete, it should sum to 1. So if I had a density estimator, and I'll use the statistics tradition of putting a little hat, P hat, on top of P, you first might want to say, well, how would I tell whether I had a good density estimator or not? And the idea is that a good density estimator should assign high density wherever the true probability is large, and low density wherever the true probability density is low. And the standard metric is called the log likelihood on a separate test data set that's also drawn from P. And so we take the log of the probability P hat of xi, the probability density, and we sum that up. And those numbers should be, the more positive they are, the better. And the actual values of the log of probabilities are often negative because probabilities are less than 1 usually, right? So we sum them up, we still get a negative number, but we want a negative number that is heading towards 0, not a large negative number. And so, so in this sense, it's a lot like standard machine learning in that you train on a training set and then you evaluate your performance on an independent test set. The same thing is true here, but instead of asking, am I getting a point right or wrong, I just want to know, am I assigning high probabilities to all the data points that are from the same distribution and low probability outside of that distribution. Okay, and I guess I'm just repeating myself here, that it's very important that we use different data, not the data we use to fit p hat, but independent data. So typically in an experiment, we'll take our data and divide it at random into a training set and a test set. We'll fit the probability distribution p hat using the training set. And let's see if I can get my pointer to stay on here. Okay, we'll use this. We randomly split it in a training test, then fit p hat using the training data, and then evaluate it on the test set. Okay, and just a little bit of a reminder for those of you, I don't know, we have a lot of different backgrounds in the audience, but a density, mu, is some sort of a function that is non-negative and can be integrated over the whole space. So it finitely integrates. And an event then is some subspace of some. We have our larger space X, and any subset of X is called an event. And the probability of an event is obtained just by integrating for all X inside E this measure mu of X, and that gives you a probability. So mu is a density, or every density is a measure, but probabilities are actually probabilities of events in the space. I don't know if, I think we might need this later in the talk, but I thought it was useful to remember that. So now let's think about our very first simplest example of a probability distribution is the normal distribution, right? And so if you work in machine learning after a while, you will have memorized this formula, which is that, right, this is the famous normal curve, and whose mean mu is at the origin, and whose variance, I think this is a standard normal, so it has a variance sigma, or a standard deviation of 1, right? And so it's basically the exponential function e to the minus, and then how far away is x from the mean mu, but scaled by sigma, squared and then negated. And so the probability, as you move away from 0, the probability drops exponentially fast. And then it has this funny normalizing thing out here so that it normalizes to 1. And then there's the cumulative distribution function. This is the integral from minus infinity up to z of p of x dx. So we're plugging in for x going from minus infinity up to z or z p of x. So we're summing all the area under this curve up to some point x, and so we get this sigmoidal shaped curve, which is the cumulative distribution function of the normal. Okay, so if I gave you a set of points and I said, well, let's do what's called parametric density, we assume that the data came from some probability distribution that is defined by its parameters. And we'll talk later about non-parametric methods, which are defined maybe in a much more complicated way. So deep neural networks, for example, are generally considered to be a non-parametric technique, even though they have millions or billions of parameters. But the point is they don't use all those parameters the way this normal distribution, for example, works. So one thing you may not have seen before is the idea of a multivariate Gaussian distribution. But if we think of x as being a vector in some that has, say, length d, then the mean is now also a vector of length d, and the standard deviation is replaced by a covariance matrix that is a d by d matrix that tells, along the diagonals, it tells how much variance there is for each individual dimension, and the off diagonals tell us about the correlations between different dimensions. So this is the formula for the multivariate Gaussian, and it's much less likely that you will memorize this one. I always have to go to Wikipedia and look it up. But given a bunch of data points, if I want to estimate this multivariate Gaussian distribution, I calculate the mean just by taking the average of the data points. So that's the same as always. And then I calculate the covariance matrix by taking what's called the outer product of the data points, right? So I take each data point and subtract off the estimated mean, and then I take that point and compute its transpose, and then take the product of those, which the outer product of two vectors actually is a matrix that's a D by D matrix, and each element is just the product of the ith and jth elements of the vector. And then we just sum those up over the data points and average them. So that's how you get the covariance matrix. You have to calculate the matrix inverse here in order to plug in into that formula. Okay, so if I were given a set of points like these points here, if I calculate these estimates, I generate these points with a mean of 2, 2. So the mean is here in the middle. And the covariance matrix looks like this. So it's got, there's a variance of 1 along this dimension and a variance of 4 along this dimension. So there's more spread on the vertical. It's not obvious because this horizontal axis goes from 0 to 5, but the vertical axis goes from -4 to 8. So you can see that it's a lot bigger. And then the off diagonal point terms are these 1.5s, so that and that's what gives it its diagonal characteristic here, right? That there's a correlation. If I know the value of x1 on this axis, that gives me some a range over x2. If x1 is very big, x2 is likely to be much bigger. If x1 is small, x2 is likely to be small. And so you can see that when I fit the distribution, I don't get back exactly the right answer. My estimate of the mean is a little off, but my covariance matrix, it's close. These are good estimates. Okay, well, that's the basic idea of fitting a parametric density to the data. And now if we had a data point up here that was an outlier, it would be assigned very low probability under this probability distribution. And so we would see that it was an outlier. Of course, we might also decide this point is an outlier because it is pretty far away from the data. But it should have, it's still part of the sort of elliptical shaped region. So it probably would still have higher probability than something over here. Okay, now the trouble is most data are not normally distributed, right? Real data are messy and have strange distributions. But one way you can deal with that is with a mixture model. So actually, I'm curious if how many people are familiar with what probabilistic graphical models. But this here is a simple probabilistic graphical model because I have two random variables. I have the variable C, and C is a discrete variable that maybe will go from 1 up to, say, well, I'm going to give an example with 2. C is equal 1 or 2. And then X is maybe in D dimensions. In my case, it will be a real valued variable that's in 2 dimensions. And so the idea of this diagram is that first, if I want to generate a data point according to this probability diagram, I first would choose a value for C from some probability distribution over C. And then I choose a value from X according to this conditional probability distribution, right? So P of X given C. And this is known as a mixture of 2 distributions. These are the distributions. They're called the components. If C equals 1, we have one distribution, P of X given C equals 1. And if C equals 2, we get a different distribution, P of X equals, for C equals 2. And then to get the probability of a data point, we want to sum up the probability that it came from the C equals 1 distribution or the probability from the C equals 2 distribution. And so we do that. We sum over the possible values of C, P of C times P of X given C. And that just gives us P of X. So let's look at an example. Suppose I took 2 multivariate Gaussian distributions. So I have this one here, and I have this one here. And then I draw, and let's say the probability C equals 1 is 2/3, and the probability that C equals 2 is 1/3. Then if I draw a sample of, I think in this case, is it 200 points? Then 2/3 of those points would come from the 0 distribution, all these points here, and 1/3 of the points came from this distribution. But you'll notice that a point like these x's here they have a probability. You can't tell, if I just gave you that data point, you can't tell whether it came from the C=1 distribution or the C=2 distribution. There's some probability that it came from both, and those two probabilities are added together. Is there a question? Oh, okay. So this is what a mixture of two Gaussians looks like. So now to fit a mixture of Gaussians, it turns out there's an algorithm called the expectation maximization algorithm that's quite good at fitting two Gaussians. You have, or fitting k Gaussians. You have to choose the number k of components that you want, and that's always a matter of guesswork. And then what you do is you create a matrix called R that's of dimension k by n, and this represents the probability for each data point xi, the probability that it came from the distribution that's for C for C=k. So if we go back here, right, if a data point like this x here would have some probability it came from the 0 distribution and some probability it came from the plus distribution. And those we can compute those and put them into, if we had an initial guess about the means and covariances, we can calculate these R values, which are called the responsibilities or the membership probabilities. And actually what we usually do is randomly initialize them so that they add up to 1. And then we go through a loop in what's called the M step of the EM algorithm. We estimate the probability of each possible C value just by adding up the responsibilities. And then we estimate the means by just adding up the responsibilities for something belonging to class K times its value. So this is a weighted average. And we calculate the covariances by taking the outer products and taking their weighted sum, weighted again by the responsibilities. So this just becomes the weights, the weighted mean, and the weighted covariance matrix. And once we have those, we now have normal distributions for each value of K. And so now we can recompute the responsibilities, which are computed this way, and repeat this process. So it's a little hard to see that, but here's a little visualization of what happens. You start out with I think I have to do this to get it to. So we start out initially with two Gaussians that were centered around 90. Let me show you that again. Oh, it is repeating. So you see at the very first iteration, the Gaussians look like two pancakes, and then one of them, it takes the yellow one almost immediately finds a bunch of points to match it, and the red one has to take care of the remaining points. The idea is in each iteration, you basically, for each data point, you say, are you a yellow point or a red point? And then you use the relative probability of those two things to recalculate the means and the covariances. And so if things go well, it converges well. It generally works pretty well if the two components are pretty well separated, like these two components. If there's a big overlap, then there can be multiple solutions. Yeah. So here's a result on our example. I used the MCLUS package in R. I'm a better R programmer than I am a Python programmer. And so the true values were 2/3 and 1/3, and the means were 2, 2, and -1, -1. What I ended up with the guess is that the mixing proportions were like this. So it didn't quite get them right. And it didn't get the means quite right either. So this is a local search algorithm, so it is not guaranteed to find the global optimum, right? Because it is just it's locally improving the estimate in each iteration. So so just let me summarize this and then I can stop and answer some questions if anyone has them. So mixture models are very cool because there's a theorem actually that if you make a big enough number of mixture components, you can fit any distribution. So it's kind of like a universal approximation language. So you can fit very complex distributions. But this EM algorithm is a local search algorithm. So if you initialize it randomly in different ways, you might end up with different answers. There is some research for some what are called moment-based methods that can find the global optimum. In practice, you use them to initialize the EM algorithm and then run it. And it's difficult to choose the number of mixture components, so you often have to try different numbers of components and then see which ones work best. And there's another potential bug here. If you imagine putting a Gaussian on a single data point, then you will get a covariance matrix that is not invertible. The covariance matrix will go to 0 because there's only one data point there. And that gives you infinite likelihood of the training data. Everything, you'll get a floating point overflow or underflow, and the program will crash. So there are techniques called regularizations where you force the variances to never get too small, and you can fix that problem. Okay, so let me stop and see if there are any questions at this point, because I've already been talking quite a lot. Okay, can everybody hear me well enough? Are we having any am I having any network problems? Yeah, going to the chat. Audio is good. Okay, very good. Okay. Thank you. All right, well, I will continue, but if questions come up, you don't have to wait. You can check them anytime. Okay, so now now let's look at a non-parametric method of estimating probability densities, right? I mean, at this point, I guess I should let's remind ourselves why we're doing density estimation. I mean, the idea is that you know, we're given a bunch of these points like this without knowing whether they're zeros or pluses, but the point is we're given a bunch of data points, and we want to build a probability model so that if we did have an outlier, like a point out here or even a point here, we would know that it was an invalid data point. Okay, so I think I am getting some questions now. Okay. Right. So that's our reason, is we basically, this is like a contour map of the probability density, and points that have very low probability, those are the ones we're going to declare to be outliers. So we'll probably get some false alarms here, but if we had a point right here, even though it's quite close to the data here, you can see that the contour lines are very tightly spaced. And so it's going to have a very low probability if it's right here, and we will correctly discover that it is an outlier. Okay, so let's move on and look at kernel density estimation. So in this case, this is kind of like the limit of having a mixture model where there's one mixture component for each data point. Now, didn't I just say that that was a terrible thing, that each data point would get 0 variance? Well, we solved that problem by using a fixed variance that we use on all of the data points. So the idea is that the probability density estimated at a point X is going to be the sum over all the data points of what's called a kernel function. And we take the distance of between x and xi, so this is our Euclidean distance between x and xi, plug that into the kernel, and then it has some kernel width or kernel variance. And so we very often will use the Gaussian kernel as our kernel, but there's a whole, you know, book full of kernels you can use. But the Gaussian generally is a nice choice. And so I guess as a picture, imagine that we had these data points that are these black lines here on the bottom. So suppose we had these 6 data points in one dimension. And what we do is we put a little Gaussian kernel, these red dashed lines, one centered on each of these points, and it has some variance that's controlling how wide it is, right? And each of these, because we have 6 points, we put 1/6 of we make sure each of these would integrate to 1/6. And how do we do that? That's because we're dividing by 6 in this case. So each of these kernels originally integrated to 1, but now we're dividing by 6. So now each kernel would integrate to 1/6. And so when we add up these 6 kernels, we'll get something that, again, integrates to 1, but it will be this blue curve that has this shape to it. And so you can see now we have a very flexible way of modeling that. And so so this is a powerful tool at least in low dimensional spaces. So the main design decision you have to make is you have to choose the kernel, but that's not super important because a lot of kernels work pretty well. The big problem is to choose the bandwidth parameter, which is the variance parameter. If you make and sometimes the bandwidth is called H in the literature. And I pulled this, I think, from Wikipedia. If you make H too small, you end up with getting a very wiggly fit to the data. And if you make H just right, you get something like this. And if you make H too big, you'll just end up with a big blob because it'll just smooth everything very much. So there are, if you take the packages, and there's a kernel density estimation package in scikit-learn, it has a routine for automatically choosing the bandwidth. And so that's a reasonable default. In low dimensions, that works pretty well. But another approach for all these kinds of we call this a hyperparameter, the bandwidth, right? Because it's unfortunately a design parameter you need to choose. You can't use maximum likelihood to fit it to the data, because if you do that, it will choose H equals 0, and you'll get one spike on every data point, right? And you'll get something that looks even worse than this. So you can't, but when you can use a holdout data set, like a validation data set. So now you have to, when you're doing an experiment, you'd have to divide your data into 3 parts: a training set, a validation set, and then a test set. And you could use performance on the validation set, say the likelihood on the validation data, to choose the value of H. So the big problem here is that kernel density estimation in high dimensions suffers from what's known as the curse of dimensionality. That is that it's the amount of data required to achieve a desired level of accuracy grows exponentially, actually, according to this formula, D plus 4 divided by 2. So basically D over 2 plus 2. And so it just explodes exponentially. So D up to about 6 maybe is reasonable, and then things start to get really bad with kernel density estimation. So that's the bad news. Otherwise, it's a beautiful and powerful tool. Okay, let me stop and take a look at this question here. How do you choose a threshold to separate between normality and anomaly? Excellent question. Yeah, so if we go back I mean, that is a very, very difficult question. In some applications, like if we're doing, let's go back to a picture of a case like this, right? In some applications, we can say we are concerned about false alarms. Like, for example, suppose we were setting up an application where we wanted to automatically shut off someone's cell phone service if it looks like their phone has been stolen or their SIM card has been stolen. We would really not want to get too many false alarms, because we will lose a customer every time we shut off their phone incorrectly. So we might choose a threshold out here that contains, say, 99.9% of the customers are inside that boundary, and then use everything outside that. Then we would know 1 out of every 1,000 normal customers, we would shut them off incorrectly. So maybe even that's not good enough. Maybe we need 1 in 10,000. So we could, in that application, you can set a threshold based on how painful each false alarm is, and you have to accept some number of missed alarms that will pass your threshold. The other possibility is in bank fraud. What they usually want to do is rank order. Let's say I have a staff of 5 fraud investigators in my bank. And they can only look at a total of maybe 50 cases a day. Each of them can look at 10 cases a day, because they have to look at people's records and maybe make phone calls. And so it takes them a long time to investigate each case. So what I can do is rank order my alarms each day and just give the top 50 to the investigators. So that's another way that often you don't have to set a threshold, because you don't have enough resources to look at them all. And you want to look at the most likely, and also the biggest frauds, the ones that look like they have the most financial risk. So that's another way. So basically, people try to avoid setting a threshold because, as I said, you get a lot of false alarms. And so you usually, now the question is, okay, effectively by determining, hiring how many investigators I can afford, that determines how many, that's basically setting the threshold, right? on a day-by-day basis. So let's see. So I think I'll say that I answered that one live. Okay. All right. Was there a question in the chat? Oh, no, okay. All right. Okay, so let's see. I was back at kernel density estimation. All right. The fourth technique I'm going to describe is actually more modern than the previous ones. It's called noise contrastive estimation. At least that's one of its names. The idea is we have our data set D, and we can and we're going to set up a classification problem in which we're going to generate fake anomaly data. So we'll label all the points that in our real data set, we're going to label them class 1. And then we're going to uniformly sample data points from a box that contains the data. So for each dimension of the data, we'll figure out its minimum and maximum values. And then, so we'll get a hyperbox or a hypercube, whatever, that contains the data. And then we can sample data points uniformly in that box. And then we'll choose some flexible machine learning model and learn a classifier to try to tell the difference between the real points and these fake points. And then we'll use the predicted probability from that fitted model as our anomaly score. That's why we labeled the anomalies 1. So the probability that it assigns to class 1 will be like our anomaly score. Now, the first time, the history of this is it was, the first paper I know of that talked about it was Pilaja, Gutman, and Hyvarinen in 2010 at the Uncertainty in AI conference. So, but it first appeared in the textbook Elements of Statistical Learning, 2nd edition by Hasty, Tibshirani, and Friedman. And this is a pretty good kind of graduate statistical machine learning book. I'm not sure I recommend it as the first book to look at when learning machine learning, but it's a good one. And I believe you can get the PDF now for free from their website. I'm sure you can get the first edition from their website. So, but they say there, oh, this is a well-known statistical folklore tradition, but nobody ever told the machine learning people about it. So we discovered it on our own. In any case, let's look at an example. So here's another mixture of 2 Gaussians that I cooked up. And let's say these are our data. Now I'll sample uniformly in the box from -6 to +6. And I just put these random samples in there, right? And now I'm going to use actually a very flexible classifier, something called boosted decision trees. And then I set a threshold of 0.5 on its predicted probabilities, and I put a red circle around each of the points that it marked as being more likely to be from outside the set than inside. And you can see it's done really quite a good job. I mean, it has, here's a false alarm right here. I think we have some more false alarms up here. There's 4 of them there. Here's another false alarm. And of course, these pluses that are in here, I mean, when I randomly sample, of course, I get some points that are inside the positive data. But they will be relatively rare inside the positive data. And so, I mean, they will lower the probability of class 0 in this region. But the 0 is kind of overwhelmed the ones in that region. So this works pretty well. Again, in low dimension, but maybe up to maybe dimension 100. Yeah, question? No? Okay. So there was let's see, I'll skip this and just say that in scikit-learn, there's a package and also an R for something called XGBoost, or I use the gradient boosting machine, or you can also use random forests for this, but you need a very flexible fitting method. So one thing that's cool about this is that if you use a technique like I was using the GBM method, and the GBM method is a form of logistic regression, and you probably haven't seen that yet in the tutorials. Unfortunately, I couldn't give this lecture next week, so but you will see it. And the idea here is that what we're estimating is the log of what are called the odds, which is the ratio of the probability of belonging to class 1 divided by the probability of belonging to class 0. Now, in this case, because we know that the probability of belonging to class 1 was the uniform distribution, this is just a constant. And so we can do some algebra on this and actually solve for the density estimator over the probability that it belongs to class 0. And so that's very cool because we actually have done density estimation using this noise contrastive technique as long as we sample from a known distribution for the anomalies. And I derive this here, but I think in the interest of time, we'll skip this part because I want to talk about this cool case study. So last week was the International Conference on Machine Learning. And one of the talks there was from a guy named John Sipple, who works at Google. And it turns out that Google has sensors in their buildings. A lot of modern office buildings have sensors in them. And their goal was to make their buildings smarter, more secure, and reduce energy use, improve occupant comfort and productivity while also improving operation efficiencies. In other words, they want to save money while not making people too uncomfortable. So they have 145 buildings at Google. They have 15,000 devices that are doing the climate control, and they have 120 million measurements, okay, tons of them. And so they've got this system. It's very blurry because this is a screenshot from his video of his talk. But down here are his anomaly scores showing that something has gone wrong with one of the, with some sensor in some building. And they actually cluster sensors that are in similar kinds of things. Like if you had an office building with 10 offices that were all in the same hall and maybe the same side of the building, so they're getting the same sunlight, then you put them in a cluster and look at them jointly on this plot. And he has a system where you can hover your mouse over this and you actually get a little explanation. In fact, that's what this is, a little explanation that says what's going on. This is another visualization of it where they say, this is an alarm. It has 0 probability of being nominal. And the main problem seems to be that the air temperature sensor in this zone is bad. Here's, they sort of have a pie chart. So they're actually calculating explanations for the anomaly. And they use a technique called integrated gradients that, again, I don't have time to talk about, but getting explanations out of machine learning techniques, including anomaly detectors, is very important. So they use this system then to issue trouble tickets, to send a maintenance engineer to look at this sensor and see if something's broken with it. So I was very impressed. They retrain their system once a week based on their sensor data. So, when COVID-19 struck and people started working from home, I'm sure they needed less air conditioning and so on and so forth. So there must have been a lot of alarms at that point, and then they changed their settings. So the last topic I want to talk about before we have the exercise is deep density estimation using flow models. And this is related to deep learning. And so I just want to try to give you sort of the intuition here. So one thing it turns out is, let's let X again be a d-dimensional vector, and we want to model its joint probability distribution. There's a rule in probability called the chain rule of probability. It's different from the chain rule of derivatives, that says that the joint probability distribution can be written as the product of a chain of conditional probability distributions. So we can write down the probability of x1, and then the probability of x2 given x1, and the probability of x3 given x1 and x2, and dot, 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 all the way down to the probability of xd given all of the previous things. So you can sort of imagine that this has a kind of triangular shape. The first distribution is very simple. The last distribution depends on all the previous random variables. But we can fit each P of x1, we could use kernel density estimation or something to estimate it. And then each of these conditional distributions we could fit using something like a linear regression or some nonlinear regression technique. And so this is a way we can represent a joint distribution. It's sometimes called autoregressive, which I think is kind of a misuse of the term, but the idea is that the probabilities of some values depend on the probabilities earlier in the sequence. That's called an autoregressive model, and at least in time series. So so if you know about linear regression, it is actually doing conditional density estimation, right? It assumes that the probability of y given x can be written as a normal distribution, a Gaussian distribution, where the value of y depends on a mean function, u of x, and u of x is then a linear function of the x values. And sigma squared will be the fitted variance of those. And so we can also do this with neural networks. We can, instead of having a linear function here, we can make a deep neural network that, that tries to estimate the mean, and then we can estimate the variance from the residuals, our prediction errors. And so that's sort of the idea of these density estimation models. And the one I'm most familiar with is called masked autoregressive flow from 3 years ago, Papamakarios and colleagues. And they use normal distributions for each of these. And there's various tricks that we don't have time to go through. But the key thing is that this is the kind of thing they're able to do is if the true probability density looks like this very weird shaped thing, they can try to fit a fitted density from a single, what they call masked autoregressive flow network, and it's not so good. But if they stack 5 of them in sequence, then they get something that fits the data pretty well. And these are the data points, the sort of the underlying data points. Basically, the idea of masked autoregressive flow is you start by sampling data points from a Gaussian distribution, and then you run them through a series of transformations until you get a prediction for the distribution. Those transformations are these autoregressive models. So there's some excitement about these, and they got some pretty good results on some test problems. At this year's ICML, there was an improvement on this. So it turns out one of the problems, if you start by using a Gaussian distribution and you transform it through a series of deep network transformations, you can only get distributions here that also have exponentially shaped tails. So they're exponentially decreasing tails. But in many real world problems, you have what are called heavy tails. So if you look at almost anything that has to do with social network data, for instance, you have very heavy tails. So you have a lot of outliers naturally, a lot of extreme values. So the tails shrink slower than exponentially. Well, it turns out you can, if you apply this autoregressive flow technique, but use the student T distribution, which is a bit like the normal distribution, but it has heavy tails, then and transform it, you can also model heavy tails using these flow methods. So so that's the end of the kernel of the density estimation techniques, and I'm really running behind here a bit. Let me stop and look at some more questions here. So what else do we have? Is there a way to quantify the cases where important false positives exist? Let's see. I guess, I mean, one thing you can try to do is, let's say we're in a fraud detection case and we have those fraud analysts who are looking at the cases that we show up and then investigating them. And if they find out, oh, that wasn't a fraud, then you've got a false positive, right? And you even have a label for it. So now we start to collect a little bit of labeled data, and we can use that to either update our threshold we're using for declaring alarms, or even do tune the fitted model. And so actually, Alan Fern and his, who's a colleague of mine, and his student Sadiki, we had a paper at the KDD conference in 2018 where we showed how to use analyst feedback to update the anomaly detector to get rid of false alarms and improve our ability to detect true alarms. So I think that's maybe the best answer to that question is trying to yeah, get feedback from analysts. The same with the Google building thing. Presumably the technician goes to the office and finds out, oh, there's there wasn't any problem there, or maybe or something unusual was happening. They were having a special event, and that's why the room was much warmer than they were expecting at 8 o'clock in the evening. Then the other question is, for mass autoregressive flows, is there a sense of how many or too many? I think again, you probably want to use a holdout data set and look at your likelihood. And when you're not improving the likelihood on the holdout, you've converged, you can stop adding layers. So that would be that answer too, I think. Okay, well, let me talk about the other anomaly detection methods. This is much shorter. There are some approaches called quantile methods, and the goal is to, instead of trying to learn an actual full density estimator that assigns correct probability densities to each data point, instead we can just try to learn a boundary, a decision boundary that surrounds, say, 1 minus epsilon of our data. And so there's methods like the one-class support vector machine is quite famous, and there's also something called support vector data description. And these are very closely related to kernel density estimators. In fact, they look like a kernel density estimator where we're assigning a different weight to each kernel. And then there's also we subtract off this constant rho, which determines where how much the boundary extends beyond the data or into the data. The thing about this is that we don't use all of the data points for our kernels, but only a subset of them that are known as the support vectors, which is where it gets its name. But it's a kernel-based method. And you solve an optimization problem using mathematical optimization techniques to get these. A third approach is distance-based methods, and you're going to get some practice with this right now. Because again, often in machine learning, actually, there's a famous machine learning theoretician called Vladimir Vapnik, and he actually was a co-inventor of support vector machines. And he has this saying that you should never solve a problem that's more difficult than the actual problem you're trying to. If you're trying to solve a problem like anomaly detection, maybe solving a problem like density estimation is more than you need. Maybe, as I say, maybe you only need a boundary, or maybe it's just enough to calculate distances. Because after all, if you look at something like these kernels here, this kernel is basically has a distance inside it, right? You take the distance from the mean, and then you run it through an exponential function. So you're basically using distances. And so maybe we should just use distance. And so if we had some distance function d, I guess I shouldn't have used d because that's been my dimension, but here I mean distance, then we can get an anomaly score by calculating the distance to the nearest data point. So I've tried to illustrate that here. Oh, this should be xq, this is my query, and maybe these are the 3 nearest points. And so I take their average distance, and that's known as the third nearest neighbor distance. And here, this point is much closer to these, so its 3 nearest neighbors are these points, and it would have a much lower distance. So then we can sort our points by their distances, and that will give us our anomaly scores. Now, sometimes you have data sets where it also makes sense to try to normalize the distances by their distances. So there's something called the local outlier factor, and it normalizes these distances by taking each of these points and asking how far away is it from its 3 nearest neighbors? How far is this point from its 3 nearest neighbors? And you can use that to kind of scale the distances by how dense the data points are in the neighborhood of the query. So that's a famous algorithm called LOF, and Irene will show you some results from that. So one question is, well, how should you compute distances? Because often the raw data that you get, Euclidean distance is not so useful in that representation. And so actually coming up with a good distance metric often is a big challenge. So one method, I mean, the simplest thing you can do is just try to scale your data points, so at least they're all on the same scale. So if you're comparing height in meters and weight in kilograms, maybe you want to rescale those so that they all have a mean of 0 and a variance of 1. And then at least the distances in height and in weight will be on the same scale. But another technique that's very powerful is something called principal component analysis. And this is a tool you should learn to use. If you have real value data, it makes a lot of sense. So if you have real value data that lives in some sort of a cloud, principal component analysis tries to basically fits a multivariate Gaussian to your data. And then the principal components are the axes of the, a Gaussian can be viewed as an ellipsoid, right? It has the shape of an ellipse. And so these are the principal axes of that ellipse. And so you can then use this to rescale your data so that it is a sphere with a unit radius. And this is what it looks like if you do that for the first and second. These actually turn out to be eigenvectors if you're familiar with linear algebra. So projecting on the first and second components, the data looks like a sphere and looks pretty Gaussian. The third component, this one here, there's not a lot of variability, and so it doesn't show up here very much. So, so that's one thing, is to apply principal component analysis and then rescale things so that they're on the unit inside basically the unit sphere. This is also called sphering the data, and then you can use Euclidean distance in that. And the advantage, if I use my height and weight example, is height and weight are correlated, so they will look a bit like this this spread out thing. And so by applying principal component analysis, you can get them so that they are uncorrelated now. And so Euclidean distance will do a better job. Another method that's very closely related is to compute what's called the Mahalanobis distance. And the idea is to fit a multivariate Gaussian distribution to your data, so calculate the mean in the covariance matrix, and then use this, what's called a quadratic form. This, if you're very good, you'll recognize that this came from the exponent in the multivariate Gaussian. But you take basically x minus the overall mean mu, and then this is the inverse covariance matrix. And it basically tells how to stretch and compress the data, basically how to weight the differences, the distance. This is basically the distance from x to the mean, and this tells how to transform it, squeeze it, and stretch it to get the same distance you would get if you had done principal component analysis. The third approach is, if you know about random forests, is to actually fit a random forest classifier to your data, because the random forest produces a similarity distance, which is based on the probability that 2 data points get sent to the same leaf in a randomly selected tree out of the forest. So it's an ensemble of regression trees. But in any case, whatever technique you use, it's important to remember that these transformation parameters should be determined only on your training data. You shouldn't cheat and look at your test data, because you really need to then apply these to the test data after you fit them. It's really part of the classifier in some sense. So you want to fit it only on the training data. Okay, and then the fourth approach that I want to talk about are projection methods, and this is the isolation forest and something called LODA. So the isolation forest is a very interesting algorithm, and you'll see in our experimental studies, it's one of the best general purpose anomaly detectors. So I do want to take some time to describe it to you. And the idea of the isolation forest is that we're going to construct a fully random binary tree. So given our training data, right, we have no class labels, so we can't fit a classifier to the data. But one thing we can do is fit a fully random binary tree. And to do that, we choose one of our dimensions, one attribute at random, and then we look at the minimum and maximum values of that attribute in our training data. And we choose at random uniformly in this interval a threshold, theta. And then we split the data according to whether the data points were greater than theta or less than theta for dimension j. And then we do that repeatedly in the next, in this child. We take all the data points that where it was greater than theta, and we send them down here. And now we choose, say, attribute 2, and we choose theta 2, a new threshold. and we split the data again, and so on. We do this recursively. And the idea is that we're going to split our data, split, until every data point lives in its own leaf in this tree data structure. And then we're going to measure the depth of that point in the tree. So we'll say that this data point xi is at depth 3. So we call it its isolation depth. So how many splits does it have to go through to get to be in a leaf all by itself? That's its isolation depth. And the intuition is that a data point that is an outlier usually will be separated from the rest of the data very quickly in very few splits. Whereas a data point that is buried deep inside all the other data, we have to split and split and split to eventually get it in its own leaf. And so we might grow L maybe as 50 or 100 or 1,000 of these trees, and we let D bar be the average depth of a data point xi. And then we can calculate, there's a formula for calculating the expected depth in a random tree. And so we use that to normalize these depths and then raise them 2 to the minus. That gives us a value between 0 and 1, where 1 would be very anomalous. And actually, a typical expected value would be 0.5 for something that was not an anomaly. So in practice, the anomaly scores tend to be in the range from 0.5 to 1. So I call this a projection method because at each step here, we're projecting the data only onto one of its dimensions and making a decision there. Another technique that does something similar is called LODA, the lightweight Allen line detector of anomalies. And what it does is it generates random projections, and these are sparse random projections onto one-dimensional data. And then it fits some sort of a density estimator. In this case, I've used a kernel density estimator. And then it does this multiple times. So we might do this 50 times or 100 times. And so given a data point like this, we can project it down onto this, this distribution. Suppose we fit this only using the zeros in this diagram here, the circles. But then we have these outliers that are the pluses, or stars, whatever they are. So if we want to score this point, if we project it down onto this one, it gets a pretty high density value. But on this random projection, it gets a low density value. And so if you have enough of these projections, and of course, real data might be 30 dimensional, and so then we're projecting it down in many different random directions onto one dimension. In each one, we fit a density estimator, and then we take the average of the surprises, the minus log density from each of those one-dimensional density estimators. And as we've seen, we can use, say, a kernel density estimator for the one-dimensional. And this is a reasonably good algorithm. So both of these methods, LODA and isolation forest, seem to work well even when there are irrelevant dimensions in the data, because they generate many projections that don't involve those irrelevant dimensions. And that gives us some protection against noisy features that are not important. So I had a master's student, Andrew Emmett, who just graduated last month, and he did a big benchmarking study to try to compare all these different algorithms. We had an early version of it in 2013 and a more recent version in 2015, and now he's done a master's on this. And we did a big benchmark using 19 different data sets drawn from a place called the University of California at Irvine. Maintains a website that stores a lot of different data sets for machine learning. Many of those have now shown up also on Kaggle, if you're familiar with the Kaggle website. And we did various things to manipulate how common the anomalies were and how difficult the anomalies were. We injected irrelevant features, and we also tried to select data points that were more clustered or less clustered. And then this resulted in 11,888 non-trivial benchmark data sets. And then we did a big comparison of actually 9 different algorithms from the literature. And you've already heard about some of them: ensembles of Gaussian mixture models, the one-class support vector machine, k-nearest neighbor, LOF, isolation forested LODA. And then we did data analysis using analysis of variance to try to understand what was important about, what determined the performance of these different anomaly detection methods on these data sets. And, you know, again, I don't have a lot of time, but I'll just give you the punchline for the algorithm effect. Actually, the number one thing that determined performance was the data set itself. And so actually the most important lesson you should take away from, or maybe, I don't know if it's the most important, but a very important lesson to take away is that there is no one best machine learning algorithm, right? That you really need, when you have a new application, you need to benchmark multiple algorithms against it to choose which one maybe works best. But if we average overall 11,000 cases, data sets, and we control for the choice of the parent data set and the difficulty of the points and all those other things, and we just look at how much of the variance in the performance was due to the choice of the algorithm, then it turned out the k-nearest neighbor algorithm was the best one, which is really quite surprising. And then isolation forest was almost as good. And then you see that quite shockingly, the one-class support vector machine, which has a lot of, it has lovely theory behind it, and so academics have been using it a lot, but it actually was not a super good performer in our experiments. We don't really understand why. So that's an important research question. So we're going to show you now the iForest and LOF, how to use them in scikit-learn, and then and have you implement the k-nearest neighbor method. So I guess one thing I want to point out is that all of these, except for this method called ABOD, use distances. So fundamentally, this question of figuring out what the distance should be is very important. And that's going to be a big issue when we move to deep learning. Okay, but I think I will stop talking, which, well, I'll answer some more questions now. And then I'll turn it over to Irene Tematelewo to lead you through the tutorial that he's prepared. But first, some questions. Let's see what we've got. Okay, practically, what is the difference between a mean AUC of 0.6 and 0.77? Okay, so I guess the first thing is if this was the only, this is how much the effect on the AUC is due to the algorithm. So this is averaging across a lot of things. These AUCs are actually terrible. If you had a real application and you were only getting an AUC of 0.75, let's say, what a way of thinking about that is that, and I didn't even stop to define the AUC. But what it is, one way of thinking about this metric is if I chose a random nominal data point and a random anomaly data point, would the anomaly detector rank the anomaly higher than the nominal? Would it assign it a higher anomaly score if I were choosing those points at random from their respective sets? So this means that 25% of the time it would be wrong. Okay, now if we had an AUC of 0.6, it would be wrong 40% of the time. So it's a big difference between 0.62, but between 0.68 and 0.777, 76, well, that's between, say, being wrong 24% of the time and being wrong 32% of the time. It's not bad, but you'd really like AUCs that are up above 0.9 because you're going to have a huge number of false alarms with this. But as I say, this is averaged over a whole bunch of data sets. And if you had a single application, I would be benchmarking maybe not all of these, but at least one of each kind, like isolation forest and one density estimation method. You know, we didn't do the noise contrastive technique. I would probably try that. And I might also try LODA because it's super efficient. And I don't know whether I would do the nearest neighbor methods. They generally take cubic time, so they're expensive. But there are libraries to make them run much faster, so that they take more like n log n time, which is the size of the data set. But in comparison, a lot of these other things take time that is independent of the size of the training data. Yeah. So did I answer that question? It seems like the variance would be useful to see as well. Yes, you're absolutely right that I'm not showing the variance in this plot. It's tricky because these are the coefficients in a multiple linear regression, and we will have a paper out that gives you all that, so you can look at how much residual variance is not explained by this effect. But what you're hinting at, and really what I was kind of saying was, if you had any single data set, there is enough variance among these methods that you would want to separately test them just on that problem. Yeah. So this is more like saying, if you had to choose some methods to try, maybe you try them in this order. But obviously other considerations like CPU time and memory. One of the problems with isolation forests is you have to store a whole forest of these trees, whereas some of these techniques, like one-class SVM, require something more like constant memory. It's a lot less. Let's see, it looks like there might be some points in the chat too. Yes. Let's see. Okay. I guess that's not relevant to us. Okay. Tim, are you ready? Let's see. I'm going to say answer live, done and done. I will stop sharing my screen, I guess, and turn it over to you.
Okay.
So I should say I met Irene at Data Science Africa in 2018 in Nyeri in Kenya. So
seems like I can't share my screen.
do I need to do something? Or someone else needs to? One of the hosts. It says all panelists, and you're logged in as me, right?
Yes.
So,
yeah, it's okay. It's okay now.
Okay.
Yeah, I will turn in my camera just to say hi to everybody.
There he is. Okay.
Hi. So yeah, I'm Professor Tom's student at the Oregon State University. So I'm gonna be leading this part of the talk on the tutorial on isolation forest and local outlier factor. So yeah, like Tom was saying, we finally met at DSA Kenya Nyeri in 2018, and yeah, now we are working together on so many projects. So yeah. So my name is Irene Tematelewo. I'm from Cameroon, and yeah, I will give you guys like 2 minutes to download the tutorial before I get started. So this is the link to the tutorial. You basically just have to go to the GitHub website and download the tutorial. It's like a Jupyter notebook. Just have to open it and we get started. Did at least one person successfully open the notebook?
Yes, one person says yes.
Okay, cool.
Okay, another person says yes.
Okay, since we don't have much time left, I will get started now. Oh, I can't. Okay, so the tutorial is about anomaly detection in credit card transactions. So like I said before, the data is from the Kaggle competition website, where it is basically the data. This is the source of the original data. It's like a heavy file of 144 megabyte from a credit card transaction from European Union in 2013. So the original data contains like 84,807 transactions, out of which 492 are frauds. And yeah, the features in the dataset are labeled V1 to V28 because PCA, the principal component analysis algorithm, has been applied to preserve the confidentiality of the clients. And here you have more details about the methods that was used to collect the data. So feel free to go to the website and download the complete data set if for more exploration. So for the purpose of this tutorial, given the time that we had, I just took a tiny fraction of the data set. First of all, because the original data set is heavy, but also because the running time was gonna be very high for the two different algorithms that we are gonna implement here. So for in this tutorial, the data set that we have contains 7,108 transactions, out of which only 20 are frauds, so accounting for 0.28% of the data. And the class in the data is like 0. The class is 0 for the nominal and 1 for anomalies. Okay, so first of all, what we are going to do, if you guys are following, don't hesitate to ask questions in the chat. I will stop and answer. So first of all, what we do is we are going to load the libraries that will be used in this tutorial, the NumPy, Pandas, that I'm sure you guys are already familiar with, given the introduction that was brilliantly done by Nema and by Nema yesterday. So the other libraries from the scikit-learn package are outlier, isolation forest, and local outlier factor. So here is we're going to load our data set, where we have here an overview of the data set on the different columns, the different features that we have. And the most important ones are the two last columns, where we see the amount of the transaction, and the class, where 0 represent the fact that the transaction was normal, and 1 is anomalies. And here we have the count of each of the samples per class. Yeah, and the next step is the distribution of the data. This is the distribution of our data. So we see that, I mean, we already knew it, but we see that the data is very unbalanced. So it will be difficult to train a classifier on this kind of unbalanced data set, because basically what the classifier is going to learn is how to classify everything as nominal, given that there's not enough fraudulent data to learn the representation of the frauds. So unsupervised learning algorithms are well suited for this kind of problem. So, and the next, I don't know if I'm going too fast, but feel free to stop and answer and ask any question. Oh God. Okay, so here we kind of explore the data a little bit just to see what's going on for each of the class. So this is the summary of the data per amount of transaction for each of the class, where here we have the summary for the normal data, where we see that the average transaction in the normal class was 91 euros with a standard deviation of 261. And for the fraud data set, or for the fraud entries in the data set, we see that the mean for the mean transaction was $31. So what we can see is like the fraud transactions were relatively on smaller amounts compared to the normal transactions. It's pretty fast, but yeah, we don't have much time. And it's also very straightforward. So, and here, what I do here is just to separate the class from the features for prediction. And here we compute the function, the function to print the performance of the model once the the training has been done. Okay, so the first anomaly detection method is isolation forest, like Professor Tom explained before. So isolation forest is an algorithm that's basically built on top of random forest with the principle of splitting the data on each of the features using decision trees. So with the algorithm takes the advantage of a bunch of trees in the forest, where each of the tree makes a prediction about the class of the data. If each of the point is nominal or anomalies, yeah, each of the trees makes its own prediction, and the final prediction is the majority vote by all of the trees in the forest. And the isolation forest takes the advantage of the anomalies to kind of isolate them pretty much, not easily, but in a good way. So the two different advantages of the anomaly are the following. So first of all, we know that generally in a data set, the anomalous examples are very few. Like in this case where we have 7,000 entries with only 20 anomalies. So there are just very few anomalous examples. And the second one is that the anomalies examples deviate significantly from the rest of the distribution. So this is an example where I kind of illustrated how the isolation forest works visually, where we see that on average, if we have this data set and we want to separate the red point from the rest of the data, normally just one split is okay to isolate this point. But given that isolation forest kind of select the feature to split the feature for the sleeping randomly, we might have this scenario where the first split of the data is this vertical line where the data is first separated like this, and on the second decision split, the point is isolated. So what is when all of the three are going to make their prediction this way, and at the end of the day, the average number of split required to separate or to isolate each point is going to be computed. And the points that are outlier or anomalies are those who are going to have like the smallest number of decisions to be isolated from the rest of the distribution. So for example, if we want to isolate this blue point from the rest of the distribution, we see that we need to separate, to have our first decision split to be, for example, this horizontal line. Then we will have a second split like this, and the third one, and we need basically 4 split to isolate this point. Well, for this outlier, just 1 split was enough. So that's the principle of isolation forest explained. And now we are going to apply it to our data set, where I use the isolation forest library of the scikit-learn. Feel free to go online on the scikit-learn documentation. You have all the details there to implement it. It's very straightforward. And then here I applied it. I just computed with the default number of trees in the forest. That's 100 trees. Oh yeah, I thought there's a question. So, okay, so yeah, so I just use the default implementation of the isolation forest, also with the default parameters, 100 trees, but feel free to play with the number of trees in your forest and see the impact or the performance on the model. And yes, the next step, I'm gonna just compute it. Yeah, this is the performance where the general accuracy of the model on our data set is like 0.96%. But accuracy in itself here is not very important to us. What we really care about is the true positive rate, where out of 20 anomalies that we had, we see that with isolation forest, we were able to successfully detect like 17 out of 20, which is pretty much, which is a good performance. But we do have some false alarm where we have like the false positive rate, which is here 252 false positive, but it's really good. I mean, but the precision, as we can see, the precision is very bad, but it's justified by the fact that we have so many false positive rate. Any question?
I've been trying to answer them in the typing while you were talking.
Oh, okay.
Um,
Yeah. So
yeah, when I answer a question in typing, can everybody see it? I wasn't sure. I assume everybody can see them, but I don't know. Yes, okay, yes, thank you.
okay. Thank you. Yes. So is there any question for the isolation forest algorithm that wasn't answered yet? Because I'm going to move to the local outlier factor. Okay. So the local outlier factor, like Professor Tom explained before, is based on the density of the point. So the big picture here, like we did for the isolation forest, is like when you have an outlier or an anomalous point here, the distance between that point and its the density of that point compared to the density of its k nearest neighbor. For this example, I used the three nearest neighbor of each of the point. So the idea is like the density of the point is inversely proportional to the distance to its k nearest neighbor, where we see that this red point, for example, is very far. I mean, the distance between each of its three nearest neighbor is pretty much high. And if we take this point, for example, and we compare the density of each of the neighbor of this point, for example, this neighbor, this neighbor has a pretty much high density, the same as this one and this other one. They all have like a high density compared to those three red points where the density are pretty much, it's going to be very, very small, because they are very far from their neighbors, so the density is going to be small. And if you remember during the presentation, Professor Tom talked about like the distance, the distance being the main metric to spot anomalies in this context. And here, this is also an implementation of the outlier factor algorithm where we built on the scikit-learn package. And here I chose the number of neighbors to be 2, and we are going to see the performance compared to the isolation forest algorithm that we explored before. Here we have a general accuracy or a global accuracy of 0.80% of 0.8, which is very different from the 0.96% that we got with isolation forest previously. And as you can see here, we have only 4 true positive. So out of the 20 anomalies that we have in our data set, or the 20 frauds that we have in the data set, with the local outlier factor, we were able to successfully detect only 4 of them. And the number of false positive rate is also very high. If you remember, where we had 252 false positive using isolation forest, but now we have 1,394, which is very high. And the recall also is very low in the local outlier factor. And if we go on and modify and we change the number of neighbors here, we are going to see that the performance is even going to get worse. Here, the true positive rate is definitely 0. So feel free to play with those hyperparameters and see the performance on the model. Yeah. And here, this is the exercise that you guys are going to do in the file that you downloaded on GitHub. There are 2 data sets. The first one is the fraud detection data 1, the one that we use in the tutorial, that I use in the tutorial, and the second one is the one that you are required to use for the exercise. So you have to implement the isolation forest and the local outlier factor on that data set, and you also have to implement the k-nearest neighbor classifier on the same data set. Yeah, you have the link to the k-nearest neighbor documentation here, and you just have to follow it, and it's pretty much straightforward. And then you have to compare the performance on the 2 different methods. So that's it. Any question? Yeah, so yeah.
Very nice. Yeah, let's see. I guess one question that's been asked in the while you were talking was about, and this is a good screen for illustrating it, right where you have it right now.
Okay.
The question is, you know, when I was talking about the sort of density-based approaches, if there were outlier points like the points that the red points that are shown here that were in the training data, they would confuse the algorithm. So if we're calculating the mean, for instance, they would pull the mean towards those outlier points.
Yeah, exactly.
The cool thing about the isolation forest is that you know, as it's randomly putting down these vertical and horizontal bars as it's is chopping up the data, it will isolate the outliers from all the other data points, and they won't have any influence on where the cuts are happening, right?
Yeah. Yeah.
And
Exactly.
so that's so the isolation forest is robust to, we say, contamination. If there are, it doesn't need to be trained on clean nominal data that has no outliers in it. It can handle that. Now, if you have outliers and you're fitting a Gaussian, that's one reason. If you know you have, you think that your like fraud detection data, it contains some frauds even in your training data, and you still want to use, say, a Gaussian or a mixture of Gaussians, then one strategy there is to use T distributions instead of Gaussians, because they do have heavy tails, and so they will be less affected by the fact that there are outliers in the data. But so that's a very good question, and it's one of the reasons that we think the isolation forest scores well on these comparison studies. Let's see. It looks like there's another question.
But I guess one of the strength of the isolation forest is also the number of the number of trees in the forest, because we think that as you have like 100 trees making the decision, they are more likely to have the correct decision at the end of the day compared to only one classifier, right?
Right. But as the dimensionality of the data goes up, how many features were in this data set again?
28.
28, yeah. So you need to have a larger and larger number of trees as the number of dimensions goes up.
Exactly.
Because the algorithm is slicing up the space at random, and you want it to have an opportunity to use every one of those features in multiple trees. And so if you had, say, only 50 trees, there could be some trees that didn't even try some of the features. And
yeah, that makes sense. Yeah.
so yeah, choosing the number of trees actually is, I have another student, Liu, who's been working on techniques for doing that.
Okay, I will stop sharing my screen so that you can finish the.
Mine, I guess.
Okay.
Let's see. This is the right place, and I say share. Oops, not that button. There you go. Okay. So I just wanted to take a little bit of time to talk about the situation. So in deep learning and computer vision, and this would also apply to speech signals as well. And that is that, okay, what is this? Okay, so because so far we've only talked about data where the data sets were in nice, meaningful features, or at least low dimensional informative features. Actually, one of the questions that came up obviously about the credit card data is that the features are not meaningful. They're just V1, V2, V3. Yeah, and that's because they've been transformed to preserve privacy. But in computer vision, of course, individual pixels in an image are almost completely meaningless, right? If I go from a 4 megapixel image to an 8 megapixel image of the same thing, hardly anything will be, there won't be any really new meaning in the image. It's just a higher resolution. And yet my dimensionality is somehow doubled. So the big challenges in anomaly detection computer vision is we have no meaningful, the pixels themselves by themselves are not meaningful. There are no easy distance metrics. If we looked at distances in pixel space, it'd be really useless. Very, very high dimension, and a high degree of what we call nuisance novelty, which is things in the background, like in this, well, I guess I should get back my laser pointer, huh? Let's see, where was that? Pointer options, yeah. So like this background here, right? There's stuff back there, and there may even be text that could cause, that would look surprising, perhaps. And it's so bad that actually state-of-the-art methods that are trained on pictures from Celeb A, which is this famous data set of celebrity photos. If you ask it whether support Street View house numbers are also faces, it says yes. It can't. It's very bad at telling that these house numbers that come from Google Street View are not faces. So that's just crazy that we have such trouble. So this talk will be, this part of the talk, I just want to briefly describe some of the techniques people are looking at. You may want to come back and look at these slides again after you've had some of the lectures on deep learning. There are sort of 5 different techniques that have been studied. Some of them start by just training a classifier using deep learning and then trying to extract an anomaly score from the classifier. Which is surprising that it works at all for reasons I'll describe in a minute. There's another strategy that's called using autoencoders. And then I showed you that a masked autoregressive flow, but there are techniques that try to use deep density estimation and learn probability distributions over images. And then there are some techniques that try to learn a distance metric and then use actually any of the methods we've described here. A lot of them use fit a Gaussian and use the normal distribution distances or the Mahalanobis distance. And then finally there's a really wacky idea that involves using auxiliary tasks. So let's take a short tour through those. So this is a typical deep learning model, right, where you start with your image, in this case 28 by 28 pixels, and then we run it through some convolutional layers, and we eventually get to something called the fully connected layer or the penultimate layer. And so this has taken the image and turned it into a feature vector that we hope is more meaningful. In this case, has 1,024 features in it. So it's not a whole lot smaller than the original image, but hopefully much more informative. And then from there, we have a fully connected layer down to 10 scores, which are called logits. And then those are normalized to give us our probabilities. And so we're predicting, given an input image, and let's say there were 10 classes, like this is taken from a handwritten digit classification problem, but Street View house numbers would also look something like this. We want it to turn on one of these outputs that corresponds to a 0, a 1, a 2, a 3, a 4, and so on, for which digit it is. So what we get actually is a probability that it's a 1, the probability that it's a 2, the probability that it's a 3, and those probabilities we'll write as P of y given x, where y is the class label and x was the input image. And of course, these sum to 1 and they form a 10-dimensional vector. Now, under the sort of in theory, training of classifier to compute this probability P of y given x is known as discriminative training because we're trying to discriminate between the different classes. The task is just to take the image x and somehow boil it down to 10 numbers that try to find the differences between the classes that can be used to discriminate among them. Whereas when we think about anomaly detection, we're more interested in something like density estimation, where we're trying to learn P of x, whereas versus classification, where we're trying to learn P of y given x. And so in some sense, learning P of y given x is not learning the thing that we sort of know from a theoretical point of view. We really want to learn what is the input distribution of the images, so that if we see an image that comes that's an outlier, we could say it's different. In theory, the classifier should be discarding all the aspects of x that are not needed to just make the classification decision. But in fact, it works pretty well to do the following. If we think of the classifier as outputting this vector, we can ask, well, which class was assigned the highest probability? That's what arg max of y means, right? Find the value of y that maximizes the probability, and then take 1 minus that and treat that as our anomaly score. So the intuition is, if the classifier doesn't assign a high probability to any class, then maybe the input image belongs to some new class that was not in the training data, and it's an anomaly. And this is sort of, I call it indecision. The classifier couldn't make up its mind what class was the right class, and so maybe it's an anomaly. But that does mean that we're really looking at points along what's called the decision boundary, right? The imaginary line or surface that's separating the zeros from the ones, from the twos, from the threes. And we're saying that points that are close to that decision boundary are the ones that we can't decide about, and so we'll declare them to be anomalies. Another measure that's used is the entropy, which is an information theoretic measure that is maximum when you have the uniform distribution, and is have a value of 0 if the distribution was assigned probability 1 to one of the classes and 0 to all the others. So the higher the entropy, also the more uncertain, the more undecided the classifier was. And these turn out to be a pretty decent baseline, as shown by a guy named Dan Hendricks in a highly cited paper from 2017. So this works pretty well, even though on a theoretical basis it should not work at all. I guess that means that our deep networks are actually not throwing out all of the irrelevant information. They're keeping some. Another thing to do is to fit a probability model to this layer here. So we have a 1024 dimensional space. We could fit a Gaussian there, and then, or a Gaussian mixture model, and then use the density there. And actually, one of the best methods there uses the Mahalanobis distance technique, is one of the ones that performs pretty well. Another weird idea is that we don't understand why it works, but it works pretty well, is to take, if this is x1 is our image, we can calculate, and suppose this surface here is the outputs from the neural network, the scores that the neural network is going to assign to the data. One thing we can do is to try to take a step, calculate the gradient, the first derivative of this surface with respect to making a change in the image. We try to change each pixel in the image by taking a small step, xq plus delta xq, a small step that would increase the probability of the most likely class, right? So we say the classifier thinks this looks something like the digit 2, so let's take a step to try to make it more like a digit 2. And we're actually going to modify the pixels by some small amount, and it turns out that, and then calculate one of the scores like the score from the previous slide. And this works surprisingly well, but I don't think we understand it. I guess the intuition is if you're on a mountain peak like this, such that a small step will take you, really increase your score, then you're probably not an outlier. Whereas if you're out here somewhere in the foothills, you take a step of the same size, it doesn't get you up to a high point. But this is a complete hand-waving argument, but it's from 2017. And there's been some more recent papers on that. Another whole family of techniques is to use what are called autoencoders. And autoencoders you can kind of think of as principal component analysis, but on deep learning steroids. So given an input X, you learn a network called the encoder that maps X into some latent space Z. And then you learn a generator, or sometimes called the decoder, that takes Z and regenerates an image from it. And you train this network to try to make this regenerated image X tilde be identical to X. And this is known as the reconstruction error. So the difference between X tilde and X is the reconstruction error. And the idea is you train this to do well on your training data, but then if you give it an anomaly, the thought is it will get mapped into the space in such a way that the generator won't be able to reconstruct the original image very well. And so this is a beautiful theory. Unfortunately, it turns out to be quite difficult to train these autoencoders to do this very well. Some people have instead tried to basically just use the encoder. I mean, you train both parts, but then once you've finished, you throw away G and you just fit a probability model in this latent space Z, like a Gaussian or a mixture of Gaussians or something. And that works somewhat. But the main difficulty seems to be doing a good job of training this. There are also things like the variational autoencoder, which train a little bit better. There's a whole, there must be 200 or 300 different kinds of GAN type networks, and some of those have been used for this purpose. But in most of the comparison studies, these methods are not the top scorers. I talked about these normalizing flow models, and one of them, which is called GLOW, Generative Flow with Invertible One-by-One Convolutions, by Dirk Kingma, who's one of the smartest people in machine learning, who invented the variational autoencoder and the atom optimizer, among other things. Yeah. So we're getting unfortunately, this is an example of one that I mentioned that can't do well. It was trained on the Celeb A data set, and this is the log probability it's assigning to data points. So over here on the right hand is higher probability, and on the lower end would be low probability. So this should be the surprises. This is where we'd want the anomalies to show up. But if we train it on Celeb A and then test on Celeb A, it's done a good job of learning the distribution of the Celeb A images. But unfortunately, if we give it Street View house numbers, it assigns them actually higher probability than the faces, instead of lower probability, which is what we would want it to do. So it just does a bad job. And this was discovered by Nalaznik and colleagues last year at iClear. So very, very disturbing results. Another family of methods try to learn a distance function in this latent space. So these are so-called Siamese networks. You basically take 2 data points, say xi and xj, and you have the same encoder network, and you encode both xi and encode xj into a latent space. And then if xi and xj belong to the same class, you try to move zi closer to zj.
But his ID was referred to as case concept name.
Use their microphone to cut this feedback. Yeah. And then there are more sophisticated, there are triplet losses and n pairs losses and lots of things trying to learn distance measures. In my group at Oregon State, we have not been able to get this to work very well. So, but if you could learn a good distance metric, that's the goal of, I mean, if we had a good distance, then the problem would be solved. And another cool thing we could do if we had a good distance, right, we would hope that outliers would be far away from the inliers in this space. But another cool thing would be to do one-shot learning or few-shot learning. Given an image that belongs to a new category we've never seen before, we could map it into this space and then use a nearest neighbor classifier to learn to classify points, new images to that new class. So this is kind of our dream, that we could get good distance functions that behave well, both for known classes and for new classes. There was well, let's see, we're running late here, right? So yeah, maybe I'll just mention there was a paper last week presented at ICML that shows some promise of improving this distance metric learning. And it was called Revisiting Training Strategies and Generalization Performance in Deep Metric Learning. And yeah, and they had some good results. And then the final technique that people have been using in computer vision is a really strange idea, but is to do self-supervision on auxiliary tasks. So so we imagine, I should mention that in a lot of the computer vision situations, we're interested in a case where we have a labeled data set with some known categories. And then, as I mentioned at the very beginning of the talk, I said that there are 2 different problems that we like to look at. One is called out of distribution detection, or OOD, and the other is open category. So out of distribution is something like the train on faces and then detect that when we're shown street view house numbers, that that's from a different distribution and we should reject it. Or given chest x-rays from the front, if we see one from the side, we should reject it as coming from a different distribution. So typically we have a labeled training data for the original, for task 1, but we also want to then make it more robust so that we can detect novel classes and out of distribution type problems. So that's why in all these methods, we were assuming we had labeled data, like we had classes here that were labeled, or we even had, in these classifier-based approaches, we trained a classifier. But we still want to have anomaly detection on top of the classifier to handle detecting data points that the classifier are far from the training data, and we shouldn't trust our classifier. So for purposes of robustness. Okay, so back here to auxiliary tasks. So the idea is to create a deep neural network that looks like this. So given the input, we probably have some convolutional layers, and then we have a latent representation here. And then we have the usual classifier, we call these heads, a classifier head that's trying to predict which class the image X belongs to. But in addition, we define an auxiliary task head that tries to predict a transformation. In this case, we might take an input image and then rotate it by 45 degrees or 90 degrees or 135 degrees or 180 degrees, or flip it, or stretch it, or do things like this. And for a task like this, we know it's self-supervised because we know what transformation we apply to the image. So if we give it, for instance, a rotated 3, we'd like the classification head to say this is the digit 3, say with probability 0.89. We'd be very happy. But in addition, we wanted to say, oh, and this was a 3 that was rotated 45 degrees, and that's with probability 0.95. Right? So we wanted to do both of these tasks at once. So this is a kind of multitask learning. Okay, so that's kind of interesting. What's the point? Well, now when we give it a test query XQ, we also apply different transformations to that query, and we run it through the network, and we see, is it accurately predicting which transformations we've applied to the query. So right, given an image, we could apply these 4 different transformations, present the image 4 different times, and see what it predicted the transformations were. Actually 5 times, because one of the transformation is 0-degree rotation. And if it's doing a good job of predicting the rotations, then we'll trust this output. We'll trust its classification decision. But if it can't do a good job of predicting which rotation was applied to the image, then we don't trust the output and we declare an anomaly. So this is the idea of self-supervision with auxiliary tasks. And why it works very well. In fact, I would say, on some tests, it is better than any of the other techniques I described here. But it doesn't work for all tasks, right? So if you think about, I don't know, the digit 8, if you rotate it 90 degrees, it still looks like an 8, and it's hard to tell that it was rotated, right? So, and if you think about the digit 6, it turns into a 9 if you rotate it. So, and if you look at natural images, if you have images of, I don't know, of a tree, it's usually upright, or a house, or a person, right? But if you have an image of, say, I don't know, a Frisbee, you can't tell much about it. Or if an image of an airplane, it could be very difficult to tell whether it had been rotated or not, because they naturally, airplanes appear in many different poses in the image. But these auxiliary tasks do seem to encourage the latent space to learn things that are semantically meaningful rather than learning random stuff from the background. So even though you could imagine some backgrounds would also give you a cue about the rotation. But experimentally, they seem to work. And so this was originally by Golan and Elyaniv, and then there's an improvement on it this year by Bergman and Hoshin. And people are trying to think of other auxiliary tasks, like if I have color images, maybe I convert them to black and white. And can the system detect that? Or maybe I change the color map, or I do various things with the colors. And that gives me different transformations. And again, maybe those are semantically meaningful and encourage it to learn more about the image structure itself. Anyway, let me wrap up this discussion of anomaly detection by saying it's a super important task that, compared to classification and regression, has not been studied very much. And as we are now more and more deploying our AI systems in, in e-commerce, in safety critical things, in medicine, in law enforcement, in space applications like the Mars rover, it's critical that we make these systems be very robust. And a lot of our computer vision and machine learning methods break down very quickly if there's some change in the data distribution, or there is noise in the data, or just the surprises of various kinds. So it's also obviously important for things like fraud detection and data cleaning. But it is also quite difficult, right? I'd say our algorithms for tabular type data sets are moderately mature. I think there's still room for improvement. And as I've said, all these techniques fundamentally rely on some notion of distance. And that's what's making it very challenging to work with images, because we need some notion of the semantic distance between images, and yet our deep networks right now are not giving us very good distances. So I would say research is advancing rapidly. There are many papers each year, but a lot of them are very experimental, and we don't have a good insight into the theory. So there's plenty of stuff to do. Okay, now I'm being asked a technical question. I don't even know what it means. Have you considered Teichmüller space as a mapping space? It may help with embeddings and distance metrics. I don't know, but I will take a look at it. Yeah, I don't know what that is. So, but thanks for the question. Okay, so let me stop sharing for a moment here. Are there any other questions? I'd love to answer some more. And let me bring up my other presentation. So now we're going to switch gears and look at an application, which is the TAHMO weather network. So this will be less technical and more fun, I hope. Well, I think the other stuff was fun too. I shouldn't say such things. Let's see, where's my sharing thing again? That's not it. I should put this into. And then, okay. So I'll turn on my video once again just to say hi, because I think we've been joined by more people. So hello, I'm Tom Dietterich, and I've been doing machine learning since 1977. So I probably should tell you some stories of the old days. But I think the future is more exciting than the old days. So I'll move into the talk here rather than boring you. But I should mention, I'm happy to connect by email, or I'm at tdietrich on Twitter, or if you'd like to connect with me on LinkedIn, if you say that you were in the class at DSA, I will connect with you, and maybe I can help people out one way or another, or just answer questions. Happy to do that. Okay, so let's talk about the TAHMO project. So the plan is I'll introduce this project and then talk about the problem of sensor network quality control, and then Irene is going to describe the sort of most advanced topic, which is neighbor regression for precipitation. So TAHMO is the Trans-Africa HydroMeteorological Observatory, and it was founded, it's a nonprofit startup company founded by a colleague of mine named John Selker. And John was a Peace Corps volunteer in Africa for many years, and has done a lot of things. He's also a hydrologist by training. And his thesis advisor was a guy named TAHMO from Ghana. And so it's not spelled the same way, but it rhymes. So this is named in honor of his thesis advisor. But John Selker and a colleague of his, Nick Van de Giesen, who was also one of TAHMO's students at Cornell University, we're looking at this map here, which is a map of weather stations that report data to the World Meteorological Organization. So the WMO is one of the the United Nations has very specialized technical organizations like the Telecommunications Organization and so on. And the WMO is the one for weather. And they collect data from weather stations all over the world. The blue dots are weather stations that are reliable and are reporting data regularly. And then the ones that are green and so on are not reporting as much, and the red ones are not reporting at all. And so we can see that we have big gaps in the data in Latin America, South America, Africa, and some parts of the Pacific. And when you don't have data, weather data, you lose some economic benefits. They estimate that the U.S. weather data network is worth several $1 billion to the U.S. economy. And one reason is because if you have good weather data, then insurance companies can write crop insurance for farmers. And that allows farmers to be very aggressive, to not worry if there's going to be a drought. They can plant their seeds close together. And then if there's enough rain, they'll get a big crop and have high productivity. And if there's poor rain, they'll get reimbursed by the insurance company, so they're not wiped out financially. So, but in Africa, many parts of Africa, there is no crop insurance available, or it's extremely expensive, partly because the insurance companies don't know what risk they would take because the weather models aren't good. And of course, another problem is the weather forecasts are not as accurate because there's not enough ground data. So the goal of TAHMO is to convert Africa from being one of the most poorly sensed continents to being the best sensed continent in the world, and thereby improve agriculture. And the goal of TAHMO as a company is to have a financial model that is self-sustaining so that it can continue to pay for keeping the network running and up to date. And we're very interested, if any of you in the audience are entrepreneurs, and you might have an idea for how weather data could turn into a product, maybe in transportation or logistics or health or something, we should talk, because we would be happy to give you, free access to the data to help you get started in return for maybe some income stream once you're successful. So, yeah. So one question that often comes up is, well, do we really need ground data? I mean, if you talk to the people at NASA, for instance, they'll tell you, oh, we have these fantastic satellites that can measure raindrops as they're falling in the air. And so we did a study looking at comparing precipitation estimates that come from the NASA GPM, which is the Global Precipitation Mapper, versus a TAHMO station we have at South Tetu Girls High School. And we can see that we have lots of cases where we measured 0 precipitation, this is in millimeters during a day, whereas GPM was predicting 40 millimeters, TAHMO was measuring 0. And we also have cases where GPM is predicting 0 and we're measuring 50. And you can see this, and there are some times when we're measuring more than 100 millimeters of rain, but GPM is only saying 10. So the R squared for a regression line is only 0.22, which is actually, given the scatter plot, surprisingly high. So I think part of the problem is that precipitation, it can be very local. And also raindrops that are measured in the air do not necessarily make it all the way to the ground. They may evaporate as they're falling. And so having ground stations is very important for getting good data. So our business plan is to negotiate a memorandum of understanding with each country, because you can't just walk in and start putting out weather stations and then take the data out of the country. Weather data, in some sense, belongs to the people in each country. And besides, TAHMO doesn't want to be a colonial organization; it wants to be indigenous. So the very first employees that we hired were people who got to know the meteorological folks in each country and negotiate these MOUs that give the government free access to the data in return for permission to collect the data. And so we help supplement whatever local data infrastructure is already there. And then we've been raising funds by gifts and grants to develop and deploy weather stations. But it's hard to get grants to just operate the network, although we are having some success now by selling the data to organizations that are funded by the United Nations or WHO and things like that. But we want to give free access also to education and research. And as I say, we're eager to collaborate with other startups who might have ideas. So here are countries for which we have MOUs. This data is out of date, so I think we may have signed ones for this, but I couldn't get authoritative information because we now have weather stations in these countries, so I hope we have signed MOUs. So we're doing pretty well. We still have a long ways to go. Our guess is that we're going to need $40 million to actually deploy 20,000 weather stations. And then we'll need about 12 million a year to keep them running. But our estimate is that there might be a $40 billion market for weather data, although I think that's maybe a little high. But in any case, most of our funding has come from the US Agency for International Development, the United Nations, the EU, and we got $1 million from IBM. And we also have a school-to-school program where schools in the developed world can buy a weather station for their school and also a weather station for a school in Africa. And then we provide educational materials and link up so they can learn something about each other's culture and weather as part of that. So let me talk a little bit about the weather stations. A standard World Meteorological Organization standard weather station costs about $15,000 or $20,000. But of course, sensors are getting miniaturized and much cheaper. And our original goal was actually one station costing only 100 euros was our original goal. So we're still, the actual price of the station itself is not 2,000, it's more like $1,000, but then it costs us another 1,000 to get it through customs and pay someone to install it and all that stuff. So weather stations, this was our first generation design. It had a lot of cables. It had 3 moving parts and 5 different subcomponents. And you know, moving parts are what break first on weather stations. So this kind of spinning cup anemometer that you see up here, let's see, I want to get my pointer back again. This is just going to break because it gets dusty and the joint seize up. And you have similar problems with the rain gauge. And also it's just wherever there's wires, they can break and so on. Our generation 3 station looks like this. So it's basically a single component here and then a data recorder. And there is one cable that connects them. So no cables is a bit of a lie. There's one cable. It's got a little solar panel and then a bunch of batteries. And so it recharges just from the sun. And then it has a cellular data antenna. So it uses cellular data for basically SMS to send the data back through a long route to the TAHMO. And so let's see, what else do I have to say here? It has a GPS and a compass. It measures temperature, relative humidity, wind speed, rain, precipitation by a drip counter. The goal was to have no moving parts at all, but the drip counter, the rain droplets themselves have to move through the system, and so the drip counter can fail. And then it measures the amount of solar radiation, atmospheric pressure, and some of the stations also have lightning detectors on it. And some stations have soil moisture. We have 5 open sensor ports, so depending on other applications, we can add other stuff. Our general strategy for placing the stations is to place them at schools and basically recruit a teacher who can monitor the station and clean it regularly, and who's interested in using weather data as an educational resource. So you could use it to teach mathematics, to teach physics, to teach meteorology, or just to teach data analytics, right? And so every school, we provide a lot of educational materials and lesson plans, and the school has access to all the data, not just for their school, but for the whole network, so they can compare with other places. And I already mentioned the school-to-school program. So here are a few little photos of deployed stations. And here's our current status. We have 586 stations as of April. There are 5 countries where we have more than 30 stations. So Mali, Ghana, Nigeria, Uganda, Kenya. And we have quite a few, actually, per capita, probably Benin and Togo, and even Burkina Faso, we have quite a few stations in. And given that some of these areas are conflict regions, it's pretty cool that we're actually operating reasonably well. I mean, we have 27 in Malawi, but of course we still have big holes in a lot of places, and we'd like to try to get more stations there. Egypt and South Africa actually have their own weather networks that are not too bad. Morocco also is not too bad, but still we would like to get lots and lots of stations in everywhere. So here's a little map for those of you who are contacting from Uganda. You can see that we have quite a few. Uganda and Kenya are really well covered. So now let's move to the topic of quality control. So a big problem with weather sensors is that we leave them out in the weather and they fail. So the solar radiation sensor can get dirty. The wind sensor, which is also known as anemometer, can get dirty or get blocked. The rain gauge can become obstructed by dust or leaves. And we also encounter some novel failures. And we've also been having a lot of trouble with poor cellular telephone connectivity, surprise, surprise, and then our batteries run down. So here's some examples of some surprising failures. A bunch of ants decided to colonize our data logger. Here's some wasps decided to build their nest right here. These little things here are the anemometer. It's an ultrasonic device that sends a signal that bounces off of this. Let's see, there's, yeah. So this is, these are the kinds of things that we just can't anticipate. And that's why we want to use a kind of general anomaly detection strategy rather than one approach to dealing with data quality control is to assume that sensor failures are a bit like diseases that have symptoms. And so maybe you could sort of approach it as a disease diagnosis problem. But instead, we're thinking about this more as a anomaly detection problem, because that way we can detect things like this that are just bizarre things. So here's our quality control pipeline. Given these Generation 3 TAHMO stations, they send their data, ideally, actually, they collect data on a 5-minute basis and send it multiple times a day through the cellular data network, and it ends up in a raw database. I think maybe once every hour for the stations that have a really good cellular signal. And then we have a system that we call Sensor DX for sensor diagnosis. DX is doctor speak for diagnosis. And then we put the data goes into what's called the controlled database, which is that it's been quality controlled. I didn't indicate there's also some traditional quality control stuff that directly that goes in parallel with Sensor DX. And then the idea is that customers will pull their data from this controlled database, and all of the data is there, but some of it has flags on it saying we think this is not a valid data point, and your customer, you don't want to use this data point. The flags also go to someone called the network manager, which is who then looks at the data and has various, sort of dashboards for presenting which stations have a lot of failure notes on them. And then he creates trouble tickets, and then those are sent out to field technicians. And we have a field staff in all these different countries who then have to go visit the station, or sometimes they can call up the teacher at the school and say, could you go take a look at this? Does it look, maybe it just needs to be cleaned. But often he has to go out and replace the batteries and stuff like that, or even replace a broken component. So obviously with COVID-19, the teacher isn't at the school, and it's been very hard. In some cases, the technicians have not been allowed to travel. So we're having quite an accumulation of failed stations, but things seem to be getting a bit better. So all of these databases here live on the IBM cloud. They're donating some cloud service storage and so on to us. So what do we want a quality control system to do? Well, the main thing is we want to identify all the sensor values that correspond to some malfunctioning sensor. And so this is actually a set of time series from some thermometers from a former student of mine who worked on sensor networks in Switzerland. And you can see that they were having problems like flat lines where the sensor stopped recording the temperature, right? Because each of these bumps is a day. The sun is coming up and going down. But you can see looks like there's some noise, really serious spiky noise on the line. There are dropouts where the radio connection is lost completely. So these are the kinds of failures that we see, especially in cheap sensor networks. If we could afford $20,000 stations, we wouldn't have nearly as many of these problems. But I guess this is part of a general strategy. Use a large number of cheap sensors and then do quality control on them and cross-check them against each other. And maybe we can get a higher quality product for a lot lower cost. So there are existing approaches to quality control. The simplest is manual inspection. And Oregon State University, we have an experimental forest called the H.J. Andrews Long-Term Ecological Research Site. They have something like 30 weather stations there. And just one of the staff members looks at the data and just eyeballs it and says, oh, it looks like something's broken here. There are other places like the Oklahoma Mesonet, the US Weather Service. They use a rule-based approach called complex quality control that I'll describe in a moment. And then there's also an approach that we're trying to use called probabilistic quality control, where we bring in probabilistic models. And in the US, that's used for what are called Rawind sondes, which are weather balloons that are launched with instrument packages on them. All of these require a lot of expert time. And they all only work if you have relatively small networks. The TAHMO network will be larger than any weather network that has ever been deployed. Even at, we have almost 600 weather stations now. That's getting close to the size of the US weather network that's run by the government. So we need, and of course, we are a lot poorer. I mean, TAHMO, the company, is very poor, and of course, all weather services are underfunded. Even in the US, they don't have enough money. So we really want something that is, well, fully automated is too strong a term, but we want something that requires a lot less human resources to operate. So what is complex quality control? Well, the idea is to write a set of rules that raise an alarm if something is violated. So one type of rule would be something like a step test, right? Which says if we look at X, let's say X is the temperature. The temperature measured at time t+1 minus the temperature at time t should not should not increase by more than some parameter θ1. So for instance, if t is 5-minute time interval, then the temperature really shouldn't change by more than maybe 1 or 2 degrees Celsius in a 5-minute period. Another thing is a flatline test. That over a long period of time, the number of time steps where the temperature does not change should be less than some number θ2. So if like the temperature goes for more than an hour without changing, maybe the thermometer has stopped working, kind of thing. It's stuck at some value. And then another thing is a buddy test. Like if you have 2 thermometers on the same weather station, you can compare them to each other and they should always be close to each other. Or if you have 2 weather stations that are near to each other, maybe only say 10 kilometers apart or 20 kilometers apart, maybe they should always be reading similar temperatures. So this is the idea. You write a bunch of these rules and then you filter the data through them. And we have a bunch, we don't have buddy tests, but we have a bunch of handwritten rules that are used to do this right now. But the handwritten rules, the problem is that it's kind of ad hoc. There's no unifying principle. You don't know when you've got enough rules that you're really catching everything. And they tend to consider each variable separately. And as a piece of software, it's hard to maintain rule systems. If you've ever had to maintain a set of rules like for like firewall rules for network firewall, it's super painful, right? The advantage is it's very practical. It's easy to extend by adding new rules, and you don't need to have any statistical model of the signals, so you don't need any training data. So the idea of probabilistic quality control is different. The idea is we're going to try to fit a probability density model to the working sensors under the, if we have data where we think all the sensors are working. And then the trouble is probabilistic quality control also requires a model of what the broken sensor, what we expect to see if the sensor is broken. But let's assume for a moment we expect the broken sensor to just be giving us random values uniformly distributed on the real line. Then what we can do is we can, if we have a prior probability, we can define a variable S. So S sub t is just a binary variable that says this sensor's state at time t is either 0, meaning it's okay, or 1, meaning it's broken. And so then this conditional probability, p of xt, given that the sensor is working properly, that's this normal distribution here. And p of xt, given the sensor is broken, that's this dotted line here. And so, and if we have a prior probability, what's the probability that the sensor is working? It's probably something like 0.99. The sensors are usually working, and broken maybe 1% of the time, or 1/100th% of the time, or something like this. Then you can do probabilistic reasoning to say, well, given that I see this observation here of a 3, what's more likely? Is the sensor working or is it broken? Well, the answer is it's much more likely to be working than it is to be broken. But if I see a reading of 5, well, now it's more likely that it's broken than that it's working. And you can weight this by probability of S. You're actually applying Bayes' rule or Bayes' theorem to calculate this, because you have the background probability of being broken or not, the probability of the observation, you divide through by just the probability of the data point itself, which is just the sum of these two. This is sort of a mixture model, right? We have one component for working and one component for broken. That goes in the denominator to normalize things, and that gives you the probability of the sensor state given the observation. So that's the idea of probabilistic quality control. Now the big problem is, how do you model the broken distribution? You've got tons of data for when the sensor is working correctly, so it's really easy to fit cool, wonderful models for correct functioning, but you have very few examples of the sensor being broken. And so, and plus you have sensors that break in novel ways, so even assuming that there is a well-defined probability distribution is a bit of a challenge. So the idea, one hack is to, and this is a term that I got from Chris Williams, who is another Gaussian process expert, and I think you had a lecture from Neil, right, on Gaussian processes from Neil Lawrence. And he calls it the junk bucket. You just define some very simple thing like a uniform distribution as your background distribution, and that's more or less equivalent to setting a threshold on the working distribution, right? You're just saying if the probability of working is above this dashed line, then it's okay, and if it's below, we'll declare it to be an anomaly. So you're setting a threshold, and as we discussed earlier, it's sometimes hard to set a threshold. Okay, so our idea was maybe we could use anomaly detection methods instead, and we could use the anomaly scores to model, because an anomaly detector will assign an anomaly score to broken sensors. Maybe we could use that instead of having to model the probability of a particular actual observation, we could just model the probability of an anomaly score given the state of the sensor. And we could even assume just the anomaly scores are going to be higher than the nominal scores. So that's our idea. And so our basic configuration of our approach is to use this simple probability model, right? We have the sensor state, working or broken, and then we have the anomaly score. So if we observe xt, we calculate the anomaly score a of t, and then we ask what's the most likely state for the sensor, which is the product of our prior belief about whether the sensor is broken or not, and then this probability distribution, the probability of the anomaly score given the state of the sensor. So we still have to come up with a probability distribution for the anomaly scores given that the sensor is broken. But so it's not perfect, but we can at least, it's easier to model the anomaly scores than it is to model precipitation and wind speeds and things like that. So I wanted to give you a little reminder about probabilistic graphical models, because I'm going to use them a bit more here. So the idea of a probabilistic graphical model is where you have a directed acyclic graph, and each node in the graph denotes one variable that we're dealing with, a random variable, and each edge is a probabilistic dependency. And so if a node has no incoming edges to it, then it's just has a distribution like this, P of X. These are called marginal distributions, simple distributions, and P of R here, for instance. And then if you have a node that has incoming arrows, it represents the conditional probability P of Y given the value of X and R. So we call X and R the parents of Y. And so it's the probability of Y given its parents. And now we can take the product of all of these to get the joint distribution over all the variables. So the joint distribution of R, X, and Y is P of X times P of R times P of Y given X and R. And for all possible values of X, Y, and R, you can plug in here and get the corresponding probability, joint probability. So that's the simple idea of probabilistic graphical models. And so these could either be discrete distributions or continuous ones. If they're discrete, we just learn discrete probabilities. If they're continuous, we learn probability densities. Okay, now suppose I want to make a query against this where I'm going to observe some variables and then compute the probability of one or more remaining variables. That's the idea of a query. So for instance, suppose I wanted to know the probability of X given Y. I can calculate from the probability of X and Y divided by the probability of Y. That's the definition of conditional probability. And how can I get the probability of X and Y, the joint in the numerator here? Well, I take the full distribution and I sum out the value of R, because if I sum, I can basically, I can sum out R in this formula. I can actually factor the P of X out because it doesn't involve R, but this term, P of Y given X and R and P of R, they both involve the variable R. So I'll have to sum out over all those distributions, and that will give me this. This is sometimes called marginalizing, because this is called the marginal distribution after removing R. And similarly, to get P of Y in the denominator, I need to sum away X and R, and that will give me P of Y. And so I can calculate this, oops, I did it wrong here. This should have been P of X given Y. I would just take this thing and divide by the denominator. And sometimes you can do some algebraic simplifications on these, and there are automated tools for doing these computations. And this process is called probabilistic inference, and it's related to logical inference. Sometimes we want to do what's called a map query. So for instance, this will be what we'll want in our diagnosis, where we've observed a variable, and now given we've observed the value of that variable, we want to ask about some other variable. So for instance, maybe I want to know what is the most likely value of X given that I've observed Y equals 0. So in the notation here, we shade this node to indicate that it has been observed. And it turns out that once we have that observed, then we need to calculate the probability of X given Y equals 0. And then this argmax says, well, we just need the value of X that maximizes this. And it turns out there are algorithms that are more efficient if you just want to know what's the setting that maximizes it. You can replace some of the sums with maxes in the inference. So those are the kinds of things that you can do. Okay, so actually maybe I should pause here and see if there are questions about that before I go on. So any questions from folks? Okay, well, we'll go ahead here. Cool things we can do with probabilistic graphical models. We can add persistence. So we can say, you know, if the sensor was working at time t, then it's likely it's still working at time t plus 1. Is there a question? No. Okay. And so we can add this so that we can have, you know, the state of the sensor time t and the anomaly score at time t, the state of the sensor time t+1 and the anomaly score time t+1. So if the sensor is working, it's probably still working at time t+1. There'll be some small probability that it will fail. Whereas if it's broken at time t, then it's probably still broken at time t+1 because sensors don't usually repair themselves. One exception is that a dirty solar radiation sensor, if there is a good rainstorm, it can clean it, and so it does heal itself. But most of the others stay broken until a technician visits. And so another thing we can do is to model the joint distribution of multiple sensors, right? And so this is a plot for a weather station in Oklahoma. We've been using data from the US to develop our algorithms, but now, because we didn't have enough data from Africa, but now we've got a lot more data from Africa, but this is an old slide. But there's a general relationship between the humidity and the air temperature, right? As the air temperature gets higher, the relative humidity will drop unless you're bringing in moisture from some other source. But if you have no wind, then you have this kind of a relationship, inverse correlation that's pretty strong. This is cool because, right, let's suppose we observed, say, a relative humidity of 45 when the temperature was 22, so right where my red dot is. That should be an anomaly, right? Even though it's well within the expected range for temperature by itself, and certainly well within the expected range of relative humidity. So if we're looking at one of those variables all alone, this wouldn't seem like it was an unusual value, right? But the fact that they're correlated and this breaks the correlation, that helps us find outliers and broken sensors really well, right? And so this is where we hope to do much better than the rule-based things, because we can look at multiple sensors together and exploit their correlations. One problem with it is, yes, this is an anomaly, but then you don't know, was it the thermometer that was broken or the relative humidity sensor, or both that are the failing sensors? So we'll come back to that thought in a moment, but that's a challenge. So this is represented this way, to have an anomaly score that takes in both temperature and relative humidity together. And then it will have two parents. It will have the state of the relative humidity sensor and the state of the thermometer as two variables. And so, and then of course, again, we still have the persistence. Another thing we can do is incorporate technician visits. So you can't really see this curve very well, unfortunately, in this plot, but this was the temperature of a sensor, and during this period of time, the technician was visiting the station, and I don't know if you can see it very well, but there was a sudden instant drop in the temperature, and then a spike to recover again, just before the technician left the station. So probably he might have been doing some calibration manipulation on it, or something like that. But in any case, or he might have been repairing the sensor. So we introduce another variable R of t that is 1 whenever the technician visits the station, and the technician. And so if the sensor was broken at time t and the technician visits, then there's a much higher probability the sensor will be working at time t+1, right? On the other hand, technicians have been known to break things when they're replacing other things. So there is also increased probability that if it was working at time t, that it was broken at time t+1. So anyway, we want that additional parent coming in here. And this we have observations because we know when the technician visits each station. Okay, so the idea of sensor DX is what we call a multiple view approach. So if you've ever studied databases, you might be familiar with this idea of a view of a database, which is like a subset of the variables. You can derive new database tables from other tables by doing joins and projections and things like this. So within each view, we then compute an anomaly score, and then we're going to combine all of those by doing probabilistic inference in the resulting graphical model. So we have 4 types of views in the experiments I'm going to describe. And I should say that this work is the result of a student of mine who graduated recently, Tadesse Zemicheal, who is from Eritrea, and he finished his PhD and is working in the US. But we have one kind of view is we just have a single variable at a single station. So this is what we've been describing. And then we might have a single variable across multiple stations. So we might have a single view. So now instead of a single variable here, I'm using a view. That might be like temperature and relative humidity combined. Well, not here, but let's see. Multiple variables in a single station. This would be like temperature and relative humidity combined. And there are two parents, one for temperature and one for relative humidity. And you also might have a single variable over multiple time points. So you might, if you want to detect things like flat lines or sudden jumps, then you want to look at the temperature at time t plus 1, time t plus 2, and combine all of those with an anomaly detector that looks at all three readings. So we have a single variable in a single station, a single variable with maybe two different stations, multiple variables at a single station, and a single variable at multiple time points. These are the four views that we looked at. Your views, we want views that don't have too many variables in them, because if you have a lot of variables, then you have a lot of parents, and that doesn't help you diagnose things, right? The trick is to figure out, as I say, when we have, we want multiple parents because we want to detect and exploit correlations, but then we don't want to have too many parents because if you get an anomaly and it has 10 different parents, you don't know which of those parents is broken, and it's hard to figure that out. So you get more diagnostic information by having fewer parents. So to design good views on a single station, we can calculate all the pairwise correlations between all the sensors. And so here's what the pairwise correlation matrix looks like. And it's showing that we have some strong negative correlations between atmospheric pressure and air temperature, between relative humidity and solar radiation. Let's see, air temperature and solar radiation, air temperature and wind speed. You can see we have some decent positive and negative correlations. And then some things that are completely uncorrelated. So these are all the different variables that are calculated in the Oklahoma things. I see I have a question. Maybe I should take a look at it. Could we use infer the likelihood that the technician actually visited the station? Yes, you could try to reason backwards. So I'll say yes, definitely. If we didn't have data on technician visits, and sometimes that data is broken, then we might say, well, could we explain this anomaly not by a sensor being broken, but by the technician having visited the station? But we should get metadata, because the technician, I mean, we try to have an app that they have on their phone. They can say, I'm visiting the station today. And yeah, so in fact, we need to know that too, because we also need to mark all the readings while the technician was at the station should be marked as invalid or suspicious. And we wouldn't want our customer to use those. Because for instance, the technician might want to pour a known amount of water into the rain gauge to check that it's working properly. And we don't want the weather station to say, oh, it's raining, it's raining. Yeah, anyway, so based on this, Tadesse chose some views. Another thing when you're looking at what good views across multiple weather stations is to understand how strong the spatial correlations are. And I believe you looked at some spatial stats models the other day. So this is sort of a version of what's called the semivariogram, right, in Gaussian processes or creaking models. So here we can see that if we have two weather stations that are 100 kilometers apart, they're going to still have pretty high correlations among their temperatures, their air temperatures. With relative humidity, if they're 100 kilometers apart, well, the correlations are not 0.98, they're more like 0.9 or 0.85. And with solar radiation, they vary. It falls off kind of linearly, but at 100, they're 0.92. Air pressure, so atmospheric pressure is super smooth over huge areas, but sometimes there are low correlations, and that could be because of a change in elevation, for instance, or stations that are very near the ocean, or could have different results. So the idea finally is we're going to get a joint probability distribution over all of these views, right? And it looks something like this: the probability of the of a station being broken, conditioned on the anomaly scores of all the views. This is for just for a single station, and the technician visit. We write as this is the product over all of the sensors at that station of this is the state changes of the sensor and the prior probability of breaking, and then this is all the evidence that we have. So for the parents of each view, conditioned on them, what's the anomaly score? So this is the extent to which the sensor states explain the observed anomaly scores, right? Parents of this view will be some of these S's. So this is how the evidence here connects to the we call this the dynamics, how the sensor states are changing. So now we can do probabilistic reasoning if we have all of these. But first we have to talk about, well, what do we use for our anomaly detectors and how do we get our probabilities? So for our anomaly detector, we're using the isolation forest. And what we do is we collected data from 2019, and then we divide the year into blocks of 20 days. This is for our Africa work. And we block it into 20 days because, over the course of a year, there are big trends. I guess I thought I had a slide in here about that, but there are big trends in the temperature, right? That every day it warms up and cools off, as we've seen. And then depending on where you are, actually at the equator, there's not so much of a big annual trend. But if you are closer to the ocean or closer to or further away from the equator, you're going to get the seasons. And so it'll be colder in the winter and warmer in the summer, but it'll be cooler in the rainy season and warmer in the drought seasons and so on. So then and so what we wanted to do is break it into periods of say 20 days where the weather is approximately stable. There's not too much of the annual trend. And then we mostly look at features aggregated either by the hour or by the day, and we calculate their mean, their variance, their max, their min, and their median, and summarize those as features, and then fit an isolation forest to all the data points that are in each view of each block. So we have a separate anomaly detector for each of these 20-day blocks throughout the year. And then when we're scoring a reading from 2020, we look up the isolation forest of the corresponding block and use that to assign the anomaly score. And that's because, of course, the anomaly detector is assuming that the data are stationary, independently distributed, when in fact they do have these trends. So by using a shorter time window, let's say from January 1st to January 20th, and from midnight to 4 o'clock in the morning, you get a block like that, and you can fit an anomaly detector to that. So then that's good. How do we fit these conditional probability model? Well, if we have n parent sensors on a view, then there's actually 2 to the power n different configurations of broken parents, right? They could all be working, which is hopefully the normal case, but one of them could be broken up to all n of them being broken, right? So that's exponentially many probabilities we need to estimate. It's another reason to keep the number of parents small, but sometimes we have 4 or 5 parents, and so one way we've approached this is to approximate this by just counting the number of parents that are broken. So if there are 0 parents broken, 1 parent broken, 2 up to n, so that means we only have n plus 1 configurations to model. So we're obviously, this is an approximation. It's assuming that if there are 2 parents broken, the anomaly scores will have some behavior that's different than if there are 3 or 1, and so on. The other thing is, how do we get probabilities, the probability of the anomaly scores when there are broken parents? Because fundamentally, using anomaly scores does not solve the problem of the junk bucket. It maybe makes it less important, but let's see, there was a question. Do we differentiate climate anomalies from weather anomalies? Yes, we're thinking here about weather anomalies, which is just that we have a surprising reading. And those of you who are familiar with meteorology and climate study know that in climate, when people talk about an anomaly, they just mean the difference of the current reading from what's the long-term expected average. Here, we're using the word anomaly in the sense of anomaly detection, that it is a low probability reading that might signal that a sensor is broken. So that's a different meaning of anomaly, right? We would expect that during a cold spell, when a weather system comes through, that there will be a temperature anomaly which is to say the temperature will be lower than normal. But that could be, from the point of view of anomaly detection, that could be a nominal temperature reading under those conditions, right? So, so it is not. So it is a weather anomaly in the sense of, or a climate anomaly, but it is not a broken sensor anomaly. I don't know if I made things clear or more complicated, but so we're really using anomaly in the sense of a statistically unlikely thing that indicates something is broken, rather than a departure from trend. But they are both kind of departures from expectation. Okay, so so we don't have enough real data with real failures in it to get good probability models. We could have just assumed that the anomaly scores are higher if and get more and more higher as you get more and more broken sensors. But we decided to take a simulation approach. So for each sensor, we think about simulated faults. So this is closer to the disease diagnosis mindset. And we insert simulated faults. So we insert flatline readings, or a bias where the sensor is arbitrarily high or low for a while, or noisy spikes into the data. And then we fit Gaussian distributions to the anomaly scores to model them. So here's an example. This is relative humidity so it just has only one parent, right? And if the parent is not broken, then you get this blue distribution of the anomaly scores from the isolation forest. And if it is broken, you get this yellow distribution. And so we see that that these distributions overlap quite a lot. So, but we fit Gaussians to them. You can see the Gaussians aren't even super good fits to these, but they're kind of conservative, so we're using them. But we might be able to improve performance by using some other distribution, maybe even a kernel density estimator. And here are some more examples of fitted ones. This is for, what does it say? Oh, air temperature. This is for air temperature, but with time scale. So air temperature over 4 time steps. So you could have the sensor could be broken at multiple of those time steps. And this is air temperature at a different station, I think. And this is joint distribution of temperature and relative humidity. And you can see the distribution with 2 sensors broken or 1 sensor broken are quite similar here. That's these distributions. Okay, so to wrap it all together, we assembled the incoming data into these view tuples. We compute the anomaly score of each view tuple, and then we can perform probabilistic inference to try to determine which sensor states best explain the observed anomaly scores. So that's this: find the argmax, so the most likely setting of the states of all of the sensors at all time steps that has the highest probability according to the observed anomaly scores. And I should say, and also technician visits should be in here. So ideally, we would do this, right? And it would be over all sensors and all time steps. But there are 2 to the power NT configurations. And also, you would have to wait until like the end of a whole year and then do a giant inference over all the stations and all the sensors for the entire year. And that's computationally completely ridiculous. And besides, you wouldn't get an answer until the end of the year. And you need to go out and repair those stations quickly. So to overcome this, we employ 2 approximations in the probabilistic reasoning. One is called search map, which is a more fast, greedy, approximate way of calculating this argmax, and the other is filter and commit, which goes by time steps. So to show you search map, the idea is that suppose I have 3 sensors at time t that I'm looking at. I'll assume to start with that they're all working. And then I can calculate the log likelihood of that. So what's the probability, the log of the probability that's assigned to all of the observations. and I might get a log likelihood score like minus 8.03. Then I consider changing the sensor state to break either sensor number 1, sensor number 2, or sensor number 3, and I score each of these. And then it turns out that this one, all of these are more likely than that all 3 sensors are working. But the one that is most likely is if sensor 1 is broken. That has a score of minus 4, which is bigger than minus 7, right? And so then we say, okay, let's consider flipping either also breaking sensor 2 or breaking sensor 3. Does that improve the likelihood? Well, breaking sensor 2 actually made it worse, but breaking sensor 3 made it higher. And now we say, well, suppose we unbreak sensor 1. Does that help? Or suppose we break sensor 3, and neither of these helps. And so we stop and we say, this is the most likely setting. So we haven't actually investigated all of the different configurations, but with only 3 sensors, we have looked at most of them, right? 1, 2, 3, 4, 5, 6, 7, 8. Actually, we have studied them all here. We have generated all, but maybe not. Anyway, because there is a duplicate here. This one and this one were evaluated twice. In any case, this is a greedy algorithm, right, that is considering flipping only 1 bit at a time. And so it doesn't necessarily find the optimal solution, but it works quite well in practice. And we compared it to several much more sophisticated methods, and this actually worked better than some very fancy things. So that's the one we choose. So here's a bigger picture of kind of what things look like. So let's imagine, and this is even a tiny part of the whole probabilistic graphical model. But let's imagine we're looking at air temperature, that this is the state of the air temperature sensor, sensor number 1, and the sensor number 2 is the relative humidity sensor. And that we have 3 views. We have a view of the temperature at the 3 consecutive time steps. So we'll say that is view number 1 at time steps 0, 1, and 2. This is view number 1 at time steps 1, 2, 3, and so on. And then this is the relative humidity also at time steps 0, 1, and 2. 1, 2, and 3, and so on. And then this view here is the combined temperature and relative humidity at time 0, the combined temperature and relative humidity at time 1, their joint distribution. So then, the idea is that we're going to define we'll look at just the sensor readings up until time 2. So sensor readings from 0, 1, and 2 allows us to calculate the anomaly scores for these nodes, and so they're shaded as having been observed, and none of these state nodes, they're never observed, right? So so now we want to do inference, and we're going to do inference over just this problem. And so we say the observation time is 2, and we're going to talk about the focus time and the commit time. So we do map inference over all 6 of these variables using search map, and then we take the conclusions, the sensor states assigned to these, and we assume they're correct, so we adopt them. And this is this idea of committing to those values, because otherwise we could wait until we've seen more things and revisit that decision, but we can't afford to do that. So we've got to commit to those. So we add these flags to the database and say we think this is the state of the thermometer, and this is the state of the relative humidity sensor. Then we get in our next sensor reading, 5 minutes later, and that allows us to now add these views, time 3, and now we do inference over these nodes here, and these are marked as observed because we've committed to their values, and we keep doing this, committing to values as we see new data, and so this is how we do our reasoning in time. So after some number of time steps, depending on the gap between our focus time and our observation time, like we could wait a whole day, for instance, before we commit. We get pretty prompt diagnosis. And so that's the basic idea for how we do our probabilistic reasoning. So at the end, so the idea is, for instance, if we had an anomaly that involved the thermometer and the relative humidity sensor, we'll just get an anomaly score, but we won't know whether it's S1 or S2 that's at fault. But fortunately, we have this other view that just involves S2, and we have this other view that just involves S1. So by combining evidence from all 3 views, we can uniquely determine whether it's just S1, just S2, or both of them that were broken. So that's the idea of that, why we have the multiple views. So there's one other problem, which is that often you want to tune the trade-off between false alarms and missed alarms, right? And there's no easy way to do that, because in this joint inference, we decide a sensor is either broken or not. And so what we do is we introduce an additional fake variable called z, and we say that z is always equal to 0, and that it's always observed. We treat it as always observed. But the probability that it's 0, given that S1 was okay, we'll call that pi okay. And the probability that it was 0, given that S1 was broken, we'll call that pi broken. So these are our two parameters. And if we set pi okay equal to pi broken, then this has no effect at all. But if we make the probability pi okay bigger than pi broken, then that's going to bias the network toward making it more likely that the sensors are working. It's tweaking the prior probability on the sensor being okay. And if we make pi broken bigger than pi okay, then it's going to bias in favor of making the sensor broken. And so we can manipulate these and repeat the inference, and we can draw out a curve. So you'll see later that we'll have a curve where we're varying pi okay and pi broken. So we did an experiment to see whether using this probabilistic inference over multiple views, whether that gives us a better fault detection than if we just used a single sensor view, which is going to be our baseline, sort of similar to handwritten rules that involve only one sensor at a time. And this, Tadesse did this on a relatively small subnetwork, just 4 stations over 2 years, 5-minute reporting interval, and just 4 sensors: air temperature, relative humidity, solar radiation, and pressure. So we have a single sensor view, but there, and then same sensor, 2 stations, 2 sensors on the same station, and a single sensor over 3 hours. And then we get a bunch of different views from that. So we have a total of 80 different views for each block of time. So there are a lot of isolation forests fit to do this. And of course, we then evaluate it by doing inserting synthetic faults, combinations of all 3 with these probabilities. And here are the results. So what I'm showing here is for each of the 4 sensors, the difference in precision between the baseline and our multi-view technique. And so our multi-view technique, and then we're using a 2-sided paired differences bootstrap confidence interval. So you can see that this interval here is much bigger than 0. So all of these are significantly better than the baseline. Especially atmospheric pressure does the best. It's 12 percentage points bigger, but all the others are too. It's maybe more sense to look at it this way, that this is the precision. So that's the fraction of alarms that are true alarms, right? And we see that we only have like 16% true alarms if we just use the baseline system that only looks at 1 sensor at a time. Whereas if we do the combined inference, we have 30% true alarms. So we've doubled the number of true alarms basically for pressure. Not quite as good for relative humidity. For solar radiation, we've more than doubled the quality. And for air temperature is the one that the baseline was already doing the best on. So I mean, the false alarm rates will obviously be like 70% roughly here. And this is why we still need a human in the loop. But it's a much lower false alarm rate than the baseline. So that's good. And here's then what we call precision recall plots, which are a common visualization where you're varying some sort of a classification threshold. In this case, we're varying pi okay and pi broken. If we make pi okay less than pi broken, then we're getting higher precision because we'll have fewer alarms, but lower recall. So precision again is the fraction of alarms that are correct, and recall is the fraction of true faults that we discover. So we can see that if we want to get the precision up to 0.3, then we need to accept something like that we're only catching 40% of the faults. Whereas if we want to get 100% of the faults, then we're going to have a huge number of false alarms. So we can choose our trade-off point on these curves. Now we think, you know, solar radiation, this is the worst curve in some sense, right? Because we're getting very low precision and really bad recall. All these guys are getting at least 50% recall. But we think we can improve that we have some ideas for how to do better. So next steps are to not use Gaussians, but to use better models for this. And the other thing is to get better anomaly detection by using neighbor regression. And so I did have these plots in here. So I mentioned, right, that a big challenge in weather data is that weather data is not stationary. It's not IID, it's changing. And these are plots from Oklahoma, from one station in Oklahoma. And we can see this plot here is the bottom axis here is the day of the year. And the vertical axis is the temperatures measured during that day. And this wiggling is due to weather systems coming through pretty much. But you can see that in Oklahoma, at least, in January is the coldest days, and then it warms up. And in the summertime, this is Fahrenheit temperatures, the average temperature is like 80 degrees, and then it cools off again, and this is December. So that's the annual or seasonal trend. So if I subtract that off from the readings on each day, then I map this onto just the hours of the day, then I get this pattern, right, which says that the temperature at midnight, it cools off, and at 5 in the morning is at its minimum, and it reaches its peak at something like 3 o'clock in the afternoon, and then cools off. And so that's the daily trend, and I can subtract that, but I still have a huge amount of variation at each hour of the day, and that variation is caused by weather systems that come through. And for 3, 4, 5 days in a row, it'll be warmer than normal, and then for 3 or 4 days, it'll be cooler than normal. And so there's that variation, and that's very chaotic. And so we can't just remove it. And so that means that that variability, we just couldn't figure out a way to remove it. I tried a bunch of things, but they often created new artifacts and false alarms in the process of trying to remove things. So there are basically three approaches. We could try to model and remove these cycles. We could do the blocking, which is what Tadesse did. Or what Irene is trying to do is to use neighboring stations that are close enough together that they experience the same cycles, the same weather systems, and so on. And so we can compare them to each other, and we don't have to do any of this trend modeling and removal. So that's what we're doing. And so at this point, I'm going to turn it over to Irene to explain this work with a specific focus on precipitation, because on the TAHMO weather network, we couldn't write any very good rules for precipitation quality control. We really need some sort of a probabilistic anomaly detection approach. And so, Irene, do you want to switch and you can share the slides and drive?
Yeah.
Okay, so I'm going to stop sharing and we'll turn it over to you. And while you're getting set up, are there questions on what I did so far? I'm doing an awful lot of talking. I didn't really give people a break anywhere in there. I meant to take a break. Maybe everybody should stretch for a moment. I'm going to turn off my camera now. Okay, someone has raised their hand. Do you want to ask a question? I'll let you talk. Go ahead. You'll need to unmute. Yeah.
Hi, Professor Tom.
Yes.
Thank you for the lecture, and as always, it's good to hear from you. I just wanted to know about the weather project and how it's happening in Uganda, and if you're getting support from the government, and maybe in terms of what you've been able to achieve from that project. Thank you.
Okay, so yeah, I don't know the full answer to your question. Uganda has not been coming up as having problems in our regular reports. So I think we haven't had difficulty with teachers helping with the stations and managing things. And of course, the government gets the weather data. So I think our relations with the government are very good in Uganda.
All right, thank you, Professor.
We actually have one station at Makerere University, and if we were there in person, we'd go out and look at it. So,
all right. Okay, thank you.
You're welcome.
Is there any question? Any more question? I will go on now.
Okay.
Okay, so after trying the different methods to like remove the trends in the data, we thought that maybe it would be interesting to use the stations with the similar variability in the network. And as you can see, the precipitation is the most important variable in the weather because, for example, in sub-Saharan Africa, 95% of agriculture rely on rainfall. And that's also true for Latin America, where 90% of agriculture rely on the rainfall. And as you can see in the right here, in the plot here, the distribution of rainfall is kind of very bizarre, where we have this heavy tail at 0, where the distribution looks more of like an exponential distribution, and anomaly detection for precipitation is very difficult. First of all, because of the 0 value, also like for more than 250 days in the year, there's no rain at all. So yeah, the days where we observe rain, they can be like a very large amount of rain, and the distribution really doesn't look like a Gaussian. So it looks, yeah, a different approach should be used for modeling the rainfall. And yeah, this is the setting. So let's assume that this is our network of weather stations, where we have the stations labeled S1 to Sn, and let R of St be the rainfall measured at station S at the time t. So we denote by R of eta of St the vector of rainfall at time t at the neighboring stations of S. So the goal here, the objective here, is to detect when the rain gauge is blocked at the station S. So the picture in the right here shows us, for example, the red dot here is our target station, and the green dot represents the most similar stations. So when we are talking about neighboring stations here, we are not talking about a distance. We are not talking about a similarity between the distances. So for example, to get those different green stations, what we did is like we fed a random forest model with all the stations as a feature, and then we ranked the most important feature, and those 5 stations are the ones that are more similar to the target station or the station of interest here. So the approach is to define the set of neighboring station NS, the green ones in the plot here, and then fit a model F to predict the rain at the red station, given the observation at the green ones. And then compare the prediction using, the prediction to the observed value at the target station, and rho here denotes the residual. So this is the probabilistic approach of modeling the unconditional mixture model here. This is a single station where we do not condition on the neighbors. Here we model the probability distribution at that station as a mixture model of the Dirac delta function and the log normal function. So here, when the rain is equal to 0, or when the probability of rain equals to 0, is modeled as a Dirac delta function weighted with the probability of rain equals to 0. So P1 here represents the probability of rain of observing a rain at the station S. So 1 minus P1 is the probability of having no rain. And yeah, so this is a mixture density model. And for the conditional probability here, it is pretty much the same definition, except that here the log normal distribution is conditioned on the observations at the different neighboring stations. So here, when we have the rain events, the probability is modeled as the Dirac delta function, but weighted by 1 minus the logistic regression, the logistic regression P1. And here, this is pretty much the same expression as before. The only difference is, the only difference between the two different expressions is the condition here. So here, P1 represents the logistic regression model with the parameters alpha, and the alpha 0, beta, and delta, and sigma squared here, the parameters of the log normal regression with covariate log, with covariate of the log R of t plus epsilon. So epsilon here is it's a very small constant that we added to avoid having to compute the log of 0. So for example, if the rainfall at one of the targets, one of the neighboring stations is 0, to avoid having to compute the log of of 0, we add this regularize this tiny epsilon value to avoid this. And how do we estimate the parameters of the probability distribution that we just defined? So like I said, P1 here is just a sigmoid function. So we just fit a sigmoid function to the data that we have, where y here equals 1 represent the days where, the days or in the data when we have the data at the station S, when the data reported is that we had a value greater than 0. So basically there was a rain observed at that station. We consider y equals 1. And when there was no rain, y equals 0. So we fit the logistic regression model and estimate the parameters alpha of this. And then how do we get the parameters of the log normal? So it is basically as defined by this expression, the weighted least square of the weighted least square on the log scale. So this is pretty much the least square regression on the log scale, weighted by the probability of having rain that is defined by the logistic regression in the first step. And how do we compute anomaly score once we have the probability distribution? So as you can see here, the CDF, or the cumulative distribution function of the probabilities that we define, is very discontinuous. So we had to define this norm for scoring the different observations, which is pretty much the negative log of the minimum between F and this. Basically F of P here is the density function as defined previously. And the second method for scoring is the negative log likelihood, where we pretty much just take the negative log of the expression that we saw before. So normally here we should, to be consistent with what we defined before, this should be normally only 1 minus P1 times the delta times the delta. But running our experiment, we remark that taking the minimum of 1 minus P1 delta and P1 F of rho given X kind of gives a better performance. So, and we ran the experiment using the 2 years Oklahoma mesonet data, and then we added the synthetic fault to simulate the rain gauge block, where we basically, the fault that we added is just turning the values at the station. Sampling some values where the report was positive rain and just turning them to 0. and then we try to detect them. So we try to answer 2 different research questions. The first one was what is the best way of scoring anomalies? And the second was which model is best? So the different metrics that we use to evaluate the different models, and it was like the precision at 80% recall, the average precision, and the area under the curve, the AUC. So this is the performance, where here the green, the blue curve represents the AUC metric. The green one is the average precision, and the yellow curve is the precision at 80% recall. And the different scoring methods are here. The mnorm.cdf, that is the cumulative distribution function that we define. This is the negative log likelihood, the kernel density estimation, the random forest regression, this is the least square regression, and the quantile forest. So as we can see here, the negative log likelihood gives pretty much the best performance. So that's the best scoring method that we found in our experiment. So now the status of this project. So now currently the precipitation model has been already deployed in the TAHMO network. So it's already functioning, and with the neighbor regression that we just defined. And yeah, for the other sensors, the temperature, the solar radiation, temperature, atmospheric pressure, these 3 different sensors are working also quite well, but has not yet been deployed. But for the temperature and relative humidity, here we model the join of the 2 different sensors, and the neighbor regression gives also a pretty good result on this joint variable, those 2 joint variables. The problem that we are still having is that the neighbor regression doesn't give a good performance in modeling the join of the wind speed and wind direction. So that's what we are, that's the active research that we are doing now, trying to find a better way to score this joint variable. As a summary, so TAHMO is like creating a very high or unprecedented size weather network, and quality control is very important given the size of the model, or given the size of the network, please. So the existing methods are not well appropriate for this size of network. Yeah, we've talked about the rule-based, the probabilistic method, and the census GX approach. And a summary for the neighboring regression. So like I said before, the neighbor regression is basically predict the value of a sensor at a station given the observation at the neighboring or at the neighboring station. Yeah, and for precipitation, we learn like a mixture model of logistic regression to predict the probability that the rain observed is positive, and we use the log linear regression to predict the amount of precipitation based on the amount at the neighboring station, and then we score the anomaly using the log likelihood. Yeah, so that's the end of our presentation. We are happy to answer the question that you guys might have.
So we have one question. He says, how have you deployed the precipitation model to the network station? Have you built a software? How do you do, I guess, how is that done? And so the answer is that the models are not actually deployed on the stations. They're deployed in the IBM cloud. So if you remember at the very beginning, I gave that diagram showing the stations send their observation via cellular data network, and it hops a few places depending. So for some countries it goes to the government first and then to the TAHMO. Sometimes it goes to TAHMO first and then the government, but it ends up on the IBM cloud, and then the code is all written in Python, as a set of services in a microservice architecture. So it's we're just using the scikit-learn and Python. So the same tools you all are using. Okay, well, that was a long series of 3.5 hours of talking, I guess. But we really thank you for your attention. And as I said, we're happy to follow up in email or on Twitter or on LinkedIn. It's very frustrating that we don't get to meet in person. But I hope we will get a chance someday. And I'll turn on my video just to say goodbye. And I hope the rest of this is good.
Thank you so much, Professor Dieterich and Irene, for the very exciting presentation and the session. It's been very informative, and to our participants, you can of course follow up with our questions in our other platforms and also via email. We appreciate for making time to give this session. Thank you so much.
You're very welcome.
Okay.
Bye-bye.
Yeah.
Bye.
Thank you. Bye. And that brings us to our next session, which is by Benjamin Akera and Andreas Damianou. Benjamin and Andreas, over to you. You'll give us a session in 30 minutes on introduction to deep learning.
All right. Can you hear me?
Yes.
All right. Okay, so I guess let's get started. I'll share my video. So this is a bit awkward because I don't know if people are hearing me or what's going on. How does this work? Okay, so thanks, Thomas, Dietterich, and the team. Your presentation has been really, really cool. But I think, let's see, how many people do we have online right now? 61 participants. Is there a way to tell how many people are actually listening? Let's see, how many people? Let's see, hands up from people in the group. Come on, let's see some hands up. I see an emoji from each country being represented there. I'll not start if I don't see more than 10 emojis. I don't know if Zoom supports emojis. All right, looks like Zoom doesn't support emojis. All right, Nigeria. Uganda, yes. Jonathan Omara, Leonard from Tanzania. Evelyn, hi, how's everybody? Gloria, I see you. Osbat. All right, so yeah, looks like we have some quorum. So let's get started. I'll share my screen. In case let's see, desktop one, whiteboard, Chrome. All right. Can you all see my screen? Let's see. All right, so can I don't know, maybe if engineer or somebody can verify that my screen is being seen because I can't see the chat now.
All clear, Benjamin, please proceed, thanks.
Perfect. So my name is Benjamin Akera, and in this talk, I will talk about the fundamentals of deep learning. My story is, my roots in machine learning began within the data science Africa community. My first DSA was in Arusha, Tanzania. That was 2017. And during this time, I got to learn from the experts and got to, attend the summer school. And this really was a revolution because I gained so much interest. And currently I'm a research intern at MILA in Quebec, Montreal, where I'm working with Professor Joshua Bengio and the team to use AI for social good and in the context of humanitarian AI. So yeah, so in this talk, I will talk about the fundamentals of deep learning, try to describe what it is. It's going to be a pretty much introductory talk, not so in-depth, but we'll see how it goes. Second thing, this talk will be split between me and Andreas. Andreas will come in part 2 of the talk, which will happen, I think, in the afternoon. He'll talk about optimization techniques and all of that. Side note, I'm experimenting with this sort of more interactive kind of presentation because this is the first time I'm doing a remote thing, and I thought I would need to have some more fancy stuff than the ordinary PowerPoint presentation. So it'll be for the first half, and yeah. So yeah, the agenda for this presentation is I will describe the introduction, the history of deep learning. I'll talk briefly about the modern deep neural networks, then the techniques and tricks that are currently being used, and a little about the applications. All right, let me just set a timer for 30 minutes. All right. Okay, perfect. So introduction to deep learning. Then I'll talk about the history, modern deep neural networks. I'll talk about the techniques and tricks that are currently being used in deep learning. And then we shall talk about the applications. So I've designed this to kind of look like the structure of a neural network. And this is done on purpose because I think each of the inputs, learning about the introduction and the history and a bit of the modern techniques, will give us some perspective on how these techniques and tricks will be used. And hopefully you'll have the ability to go build artificial general intelligence or something. Yep. So feel free to ask any questions if something is confusing halfway. Too bad I can't seem to see the chat, so I'll keep checking every 10 minutes or so. All right, so what is deep learning? So there's so many definitions on what deep learning is, and I couldn't find one more encompassing as the one on Wikipedia. So sorry if I'm not citing whoever this is from, but I think Wikipedia clearly describes it as a broader family of machine learning methods based on these things called artificial neural networks with representation learning. So learning in deep learning can be either supervised, semi-supervised, or unsupervised. So let's go deeper. What do we really mean by representation learning and hierarchical representation learning? So in deep learning, like we said, it's a class of machine learning methods that aims at learning feature hierarchies. And so what this means is that each layer of the hierarchy within a neural network kind of makes it easier to solve the problem for further layers. So in this example, we can see that in the first layers of the neural network, we have inputs, say our data, and these inputs could be like images of people's faces. And if the goal is to do some kind of facial recognition, the first layer of our neural network would be responsible for extracting features like edges. So you can see some edges, some very, very minimal shapes within the input data. The intermediary layers would be responsible for extracting a little more fine-grained features, like say you can see somebody's eye, some noses here and there, ears and whatnot. And then the final layers would kind of have more really fine-grained things like the actual faces of people. And so you can do classification and say, this face belongs to Benjamin, or this is Sierra, or this is engineer. You get the point. Right, so one thing to note is that deep learning is not a silver bullet, right? There has been so much hype, not exactly hype, but there's been so much in the media and everything with a focus on how deep learning is breaking barriers and whatnot. But it is just one tool in our quest for artificial intelligence. It is very powerful, but it doesn't mean that it will solve all problems in the world. Okay. Yeah. So let us try to see the history of deep learning, right? So the history of deep learning goes way back, even way before, say, 1958. But one of the key turning points was in summer of 1958 when Dr. Frank Rosenblatt had this paper in Research Trends, okay? And so this paper was released in the summer of 1958, and it had this very catchy headline that said, "We are introducing the perceptron, a machine which senses, recognizes, remembers, and responds like the human mind." And you can imagine what this kind of abstract, you know, in 1958 would mean. This was so mind-blowing, and people really wondered, what is this Rosenblatt is hypothesizing? And it's easy to think about. Maybe they overhyped it at that time, but it was kind of interesting because in order to claim that you have a framework that reasons like the human mind, that means your claim is really, really interesting, right? So actually in 1958, that whole the editor's note say that paper was the whole, like it was the whole point of discussion in that edition. So let us put this into context, right? So brains are really complicated achievements of nature, all right? And if we provide a framework to explain what's going on in the 86 billion neurons in the human brain, that is something really, really phenomenal, right? Nobody really understands how the brain works in depth, and it is one of those things that are really complicated for even current research in neuroscience to explain. And let us see what this means. If you look at the brain of a smoky shrew, this is a very, 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 very tiny sea creature, right? It is very small and weighs about 0.176 grams. But the brain of this contains 36 million neurons, at least. I mean, this is an estimate, right? If you look at the mouse, around here, it is about an average mouse. The ordinary ones, at least, about 0.416 grams. But these mice have about 71 million neurons, right? Looking at other a bit more huge mammals, we have a guinea pig with about 250 million neurons, right? But then when we come to the human brain, we have 86 billion neurons, right? 86,000 million, that's 86 billion neurons, right? And it's kind of hard to imagine what is going on inside these neurons. And so Rosenblatt said, in his hypothesis, said his perceptron could think, reason, and do whatever the human brain was capable of doing. And so you can imagine what this meant. So let's zoom in what this really entailed, right? So if you looked closer into what the biological neurons actually look like, we realize that the biological neurons are connected, right? They're connected and look sort of, you know, like a connected kind of system where we have the cell connected to another cell by these things called dendrites, and then dendrons that are passing information from one cell to the other. And this is what sort of makes up the basis of the neural system. And so from this, Rosenblatt said, maybe we could model the perceptron mimicking such the neural pathways in the brain, okay? And so let us look at what the perceptron really looked like. So the perceptron in simple terms did something like this. We had sets of inputs, right? Say x1, x2 to xn. And then we had these things called weights, which is symbolized by these. And then these inputs and their corresponding weights were summed up and returned into an output. So if at the end of this talk, there is one thing you should remember is a perceptron, or this fundamental perceptron, is made up of inputs multiplied by weights, and then a bias term added to them, and then passed on to the output. So just think of inputs times weights plus bias, okay? Right, so that is just a very brief history of deep learning. So I will pause to see, I mean, this is not a very exhaustive history, but I'm happy to see if anybody has any questions. Let's see in the chat. Hopefully I've not been talking to myself the whole time. Okay, how do I check the chat? Is there any question? Okay, no questions. All right, so I will move on to the second part of my presentation that will be a bit more detailed-ish. So detailed, but it'll kind of try to answer the question of why deep learning and why is it so all right, let's share my screen. Okay. All right, so.
Ben, I see a hand up.
Oh, there's a hand up. Let's see, what is the hand up saying? Sorry, Zoom is a bit unintuitive. I'm trying to figure it out. Where is the hand up?
Ben, I can help here.
Yep.
I think.
Francis can go ahead and talk.
Yeah. Please, how have you deployed the perception? Yeah, to the network station. What? Sorry, is this my question?
That's for the previous talk. I think there was a gentleman called Francis who wanted to ask a question.
Francis, could you ask the question? If you can ask the question live, I'd be happy to answer. Is it still there? I'll give him like 4 seconds to ask. All right. Okay, so I'll just continue in case there is a question that I'm not seeing. Sarah, if you don't mind, you could stop me halfway.
Yeah, can I ask you one?
Yep.
How much is neuroscience feeding into machine learning research now, if at all?
All right, so that's a very good question. So the overall goal, remember, of artificial intelligence is to mimic what deep learning in general is to mimic what biological neurons are doing, right? And a lot of what we see in deep learning currently, say things like backpropagation, which I will talk about in the future slides, and things like how this just the physical connectivity of neurons is inspired in part by neuroscience, right? So in current times, we're trying to, there's some questions that we still do not have answers to in deep learning. Things like how do we do something called credit assignment? In our brains, we do have a way that we know how neurons are, somehow, somewhere, neurons are assigned credit to sort of solve specific problems. I don't know if I'm using the right words, but there is this whole thing called credit assignment that is that people are trying to kind of figure out. And I've had people talk about it. I'm not saying I'm an expert, but it has kind of come up in the different things I'm reading about. Other things like causality. How do we measure things like cause and effect, and how do we see, I think, how do we measure causality in, as it is done in neuroscience? How can we replicate that in artificial neural networks and deep learning? And thirdly, I think one of the things I've seen pop up more recently is the question of consciousness. How can we model consciousness as it is in human beings within deep learning? And Yoshua has this paper called the Consciousness Prayer, which is trying to use inspiration from the way human beings make decisions, right? He had a paper at NeurIPS last year called System 1 to System 2 deep learning. And he's proposing that if we can do something like slow-paced learning, that just like the human brain does, or how human beings reason, then it could kind of solve problems better with deep learning. And yeah, so I think either way, it's a mix of there is a lot of inspiration coming from neuroscience into deep learning currently. I hope I've answered your question. Right?
Yeah, thanks a lot.
All right, cool. So let's go a bit deeper into how this deep learning thing works. Okay. So, like I said earlier, deep learning is all about hierarchical representation learning, and you're already seen this. We have within each layer we have more fine-grained refinements of the input data, right? And so you'd ask yourself, why is deep learning very popular right now? And it seems to have solved some of the problems that were being faced by previous or other machine learning algorithms or techniques. And one of these is that in other techniques, usually you would have to hand engineer very many features. Say if we wanted to build an algorithm that can recognize faces, we had to hand engineer things like extraction of textures, extraction of color, extraction of shapes, and all of that. So most of these things are hand engineered. And if you're to think about it, the search space of features within an input data set could be immense and very huge, right? And so the question is, that deep learning kind of gave us, the answer that deep learning gave us was the ability to learn underlying features directly from data without necessarily having to hand engineer things here and there, okay? So another reason why deep learning is currently very popular is that we've had some kind of big data revolution with the internet booming and things happening all over the place. It is easier to have very, very large data sets. One of these data sets that is popular is called ImageNet. And ImageNet is this huge data set that contains, I think, 1,000 classes of everyday objects, right? And ImageNet and so many other data sets are becoming more and more popular. And it's easier to kind of build algorithms that can learn from this big data. It's also certainly become very easier to collect data. Like in Thomas's talk, Professor Tom, we saw that he's collecting data from weather stations from all over the world. And I don't know if this could have been possible, say 60 years ago. How would it have been possible to collect data and store it and transmit it from one place to the other, right? From the source of the data to where it could be processed and analyzed. Another reason is hardware has become really cheap. Most of you are using computers that have GPUs in there and CPUs that are very, very advanced, certainly more advanced than what was used to take man to the moon in 1960 something, right? More importantly, there are these things called GPUs, graphical processing units, that have shown the immense ability to do large-scale computing, right? And thirdly, there has been a revolution in the software that has that can do deep learning. I don't know what Professor Dietterich was using in 1977, but it must have been some really complicated, I don't know, C library or something. But nowadays we have things like PyTorch and TensorFlow and Python and NumPy and Keras that can help us do deep learning, right? We have new models being released every day. Like if you look at GitHub, you'll see benchmarks after benchmarks being broken, right? And we have toolboxes like, say, deep learning toolboxes that have all these pre-packaged solutions to do things like classification, object detection, segmentation, and different other tasks. All right, so that is a bit of the other stuff. So I'll start with the part one, mathematical intuition. Let us try to build a mathematical intuition to see, to kind of understand what deep learning is, what the perceptron is, and how it's working, and all of that. Yeah, so like I said earlier, if you look at the biological neuron, we have the cell body, we have dendrites, we have the axon, and compared to on the left B, we have the artificial neuron that has inputs represented as X1, X2, up to Xn, right? And then in here, we have something called an activation function that does something. It kind of processes the input, the received inputs, and then takes it out to our output represented by Yi, right? Let us look at it closer. So the first, this whole movement of inputs to the activation function, Fx, to the output is something called forward propagation. Think of it as how, forward propagation, inputs moving forward through a network, right? So imagine you have our inputs, X1, X2, and many inputs until Xm, right? We'll define this as inputs. And then we have these things called weights, W, which we shall represent by W1 up to Wm. So for every input, there is an assigned weight to it, okay? So the weight can represent how important this input is, right? And then we have a weighted sum of the inputs and their corresponding weights, right? So the weighted sum of this is passed into this activation function that does something called nonlinearity, right? So by this, I mean, it kind of transforms the weighted sums of the inputs and the weights into a nonlinear feature space, which I will explain later. And then the output, which is represented by Y hat. So there are so many other notations used, but this is one of the easier ones that is just meant to build mathematical intuition behind this, right? So this is the output. So mathematically speaking, you'd see the equation represented like this. Y hat is equals to F, which is our nonlinear activation function, which is passed like, okay, the weighted sum of each input and its corresponding weight is passed into the activation function, right? Yeah. Let us look closer. Usually there is this thing called a bias term, which I here have represented by W0. And the bias value, think of it as, if you remember linear, what is called linear algebra, we had the equation of a straight line when we had y equals mx plus c. Thus, the bias value is the equivalent of the intercept, right? And what the bias value does is it allows us to shift the activation function to the left or to the right. And this might be critical for the successful learning that is done in the perceptron, right? So I'll just push this again down your thoughts to remind you that what is happening in the perceptron is inputs times weights plus bias, and then passed on to the output. All right. Okay, so usually we notate, let us look at the notation here. In linear algebra terms, the y hat is passed on to the activation function. W naught represents the bias, and then x's is a matrix, a vector of different inputs. So we can represent the capital X as a vector of all the inputs, and then W as a vector of all the weights, right? And so in linear algebra, when we multiply each value of the X vector and each value of the W vector, it's kind of equivalent of it. It's called the transpose. And usually also this capital T thing to represent a transpose. So it means X times W, right? I don't know if there are any questions at this point, but I think I hope this has been clear. So let us look closer into what this activation function thing is, right? So most neural networks do some kind of.
There are some questions on the Q&A.
All right, let's see. What is the question? Q&A. I don't know how the hard time using Zoom. I can't find the Q&A. Let's see. I'll just, all right, got it. You talked about deep learning being used in unsupervised learning. Can you give some examples, please? All right, so I'll give some examples of unsupervised deep learning, right? A common one is, so let's, I'll try to add, to those who don't know what unsupervised learning is, I'll give the context of, from a point of, let me just describe the whole shebang. So we have this thing called supervised learning, which means in simple terms, we give labeled examples, labeled training examples. So we have, for each input, we have a corresponding label to it, right? So usually, say if you want to label faces, you would label each person's face with a corresponding name, and so on and so forth. And in unsupervised learning, we're trying to use unlabeled data. So we have data that has 0 labels. It's just, say, a bunch of X and Y values. And what we're trying to do is identify patterns within this unlabeled data. So an example is, say you have a bunch of documents and you want to, say, identify what are the clusters, cluster these documents by maybe context or whatever, or something like that. That is an example of unsupervised learning. So in deep learning, unsupervised learning has been used in things like, I think there's this thing in natural language processing called, is it called the bag of words model, where we have, no, it's called word embeddings, right? Where we have, how to explain word embeddings? We have this huge vector space. I'll share my screen to that area that I'm talking about with embeddings. All right, so in deep learning, right, we have this huge vector space of, say, words that represent different things like city, food, feelings, body parts, and stuff. And so this is unlabeled data, and what has been used is that we can actually find vector representations from this data And we see that words that appear closer in semantic to each other, like you'd see things like cities clustering closer to each other, things like foods clustering closer to each other, right? And so on and so forth. That is one example I've seen a bit of unsupervised learning, but I could be, yeah, I think, yeah, that is one popular example. I hope that answers your question. Let's see if I have another question. Could you explain the function of the bias value again? I didn't quite get what it does. All right, so the bias value in deep planning. See how I can share my screen again. Okay. How to explain this? So I don't know if you remember something in from linear algebra. We had the equation of a straight line as y equals mx plus c, right? And so what the equation of the straight line did was it kind of drew, it drew a line to kind of represent a division or a separation between two classes, right? Either a division between two classes, or it helped us know that at a specific point in this line, we can tell what the values are, okay? And so in linear regression, we had that C, the intercept that would help us vary that straight line either up or down, or to kind of help us know where it helped us vary the input, right? So that, think of the intercept as the equivalent of the bias value. But if anybody among the panels can explain this better in the panel, like I'm sure we have experts that can really explain this. I'm happy for somebody to help. Right? Anybody? I don't know if my explanation has been clear enough. I might have not explained this. All right. Weights are assigned to each input. What informs the assignment of these weights? I will explain this in the slides coming next, right? But to give you a high-level thing is initially these weights are initialized randomly, and then as the model or the perceptron or the deep learning model is being trained, these weights are adjusted until the perfect values of the weights can give us a perfect prediction. All right, it's already time, 30 minutes. All right, I'll just explain the activation functions again, and then I will take a break and answer the questions and then see if we can proceed with the next thing. So the activation functions, like I said, help us do something called nonlinearity. The commonest one is called sigmoid. And for sigmoid, to explain what it does is that for every input value of X, what it will do is it will squish the output between 0 and 1, right? So think of any big number, whatever it is, it will be squashed between 0 and 1, right? And this is commonly used for things like classification tasks, where you need to have a probability assigned to an output, right? Another example is the tan edge, the hyperbolic tangent thing. That does, and what it does is it squishes every input value between -1 and 1. And then a commonly used one in deep learning is called ReLU, which is called rectified linear unit. And what it does is that for every input value, it either returns that value or 0, right? Yeah. Yeah, so that is the activation function. Now let us look a bit closer at what is actually happening. Let us replace the weights with actual values. So now, like you asked, somebody asked in the chat, how are these weights done, created, or how are they assigned? So I've randomly assigned these weights. People have done research on ways to do something called initialization of neural networks. The ways that people are doing, I think the popular ones are, one is called Hay initialization, the one is called Xavier initialization. And what they do is they've figured out ways to initialize these weights. But this is, okay, it's not really random, but this is 3 and -2. And just say assume it's random, right? I had no preconceived biases to use this. So we have the weight 3 assigned to x1, and then the weight -2 assigned to x2. And then we have 1 assigned to our bias, right? So in our,
Ben,
yeah?
Ben, just a reminder on the time.
Right.
It would be good to have a break and then we continue.
All right. So I guess I will stop here. We shall have a break and then hopefully we shall continue in the
Okay.
future discussions.
Oh, okay, thanks, Ben. Sorry for stopping you like that, but I think we need a break. Yeah, but thank you for the insightful introduction to deep learning.
Yeah.
And we look forward to to the other parts after the break. So we shall have a break for 30 minutes. And then remember that we are going to be using a different link. And every one of you, I think, has the link in their email. But for the panelists, you'll just be joining. And yeah, I'll leave this webinar running for another 10 minutes for those who want to ask, engage Ben in the question and answer, but you're free to go, such that we resume after 30 minutes. So at 12:45, we shall be back. Thank you very much.
All right, so I will stay in the chat to see if I can answer questions and see if there are any questions. You don't feel obliged to stay. You can go for the break. Go grab some tea because we're just getting started. For follow-up stuff, we shall have an afternoon session with Andreas, where we shall go a bit more in depth on these things. So I think this has been to whet your appetite. So see you all in the afternoon.
Okay, bye. I'll just close this for now.
Right.
Yes, there are no questions.